Okay, hello everybody. So welcome back to a new day of the Grayscale School. So now day 4th. So we will do some magic with Kokkos on CPU for now. So it's a new thing in Grayscale School. So we'll use Kokkos which is a framework to work on CPU and GPU, but now we will focus on the CPU part with Paul and with Thomas here. Of course, we'll not spoil you too much, but that's really interesting technology. So, Paul, it's up to you.
Thank you, Pierre. So yeah, welcome everybody to the Grayscale School for the Kokkos session. So with my colleague Thomas Padiolo and myself, Paul Zena, we are both from CEA. So we will talk about Kokkos on 2 days. I would like to first thank the authors of this tutorial. So Mathieu Lobé, Paul Zena, myself who contributed, Paul Ganet, Hari Prasad Kanan, Thomas Padiolo, my colleague, and Travis Marvani, we both wrote the slides that you will use today. Okay, let's continue. So this is the session for Kokkos. So yeah, it will take place in 2 steps. First, the CPU course, which is today, and next week, the GPU course, so on Thursday the 2nd. And you need to attend both sessions. That's a really important point, because today we do just the CPU part, which means that the code that we'll write in Kokkos today is not complete Kokkos code and will not work on GPU. So be careful to attend also the second week, the second sessions, because we will complete what you will learn today. I would like to give special thanks to start with to first David Chamon, who used to present the SYCL course at the Grayscale School. His course was a great source of inspiration for today's course, so I would like to thank him warmly. And also Francesco Risi, who made the slides for the Kokkos algorithms API. Both are not part of CEA. So this is the menu of what we will go through today. So I won't go into too much details into it, but the idea is that this morning, so everything which is on the left, we will do the first steps in Kokkos. We will use the serial backend, so we won't have any much difference in terms of how the program is executed comparing to sequential implementation. But this is a good opportunity to start doing Kokkos, to start to do Kokkos and check that everything is right. I mean that our program works as before. So we go through the data containers, the parallel constructs, and for the afternoon, we will move to parallel CPU backends, and we will do a bit or more of optimization with SIMD functions. All right, so let's start talking about Kokkos. So, you know, there are many programming models. The Grayscale School is a very wonderful opportunity to learn about a handful of them, but you may imagine there are much more programming models that you will see in those 2 weeks. And the question is, okay, but how to choose one programming model which is suited for your needs? And there is one interesting set of metrics, which is the performance, portability, and productivity metrics, which is, I would say, a good strategy to find what framework, library you want to use. So the performance, portability, and productivity, I give more details. So performance first is the ability to get the best performance on a specific hardware, which is very reasonable. We want our program to run fast on a given architecture. Portability is the ability to run the same code on different hardware without having to change the code, to adapt the code too much. Yeah. And productivity is the ability to write code quickly and easily. The ability to maintain it and to extend the code without having to, scratch your head too hard. And the ability to leverage architecture optimization. In other words, is how easy it is to use this library, this programming model, to achieve your goal. And yeah, the P3, performance, portability, productivity, you have 3, you pick 2. You cannot have all of them, unfortunately. This is actually a metric that developers want. But we are not usual developers, we're also developers for science, or we work with people who do science, and we want a bit more in terms of what a library can give to us. We want maturity, we want libraries that are production ready and not obscure experimental research products. We want community, we want a library, a programming model which is used by other people that has contributors, that offers support, that has documentation, up-to-date documentation, that has examples, tutorials, etc. Which is really important because when you use a new library, a new tool, you got a problem with that, like you don't know, you want to do something, you got a bug, something. You want to find more when you type the description of your error, more than just having the GitHub page of the project. You want to have forums or communities, something like that, to give an idea that the project is alive and more alive. And I was taking developers for science, I was talking about that, which the idea is the program that we make, CFD solvers, particle interaction cell solvers, etc. They are here for the long run, for a dozen years, 10, 20, 30 years sometimes. And we want to side with programming models that will last as long as our program, right? So we want a program that are here for the long term, that will have maintenance, they will have bug fixes, they will have updates, sponsorships, etc. And then we want also interoperability for our programs. Nowadays, you want to side everything with AI, but also ability to have, I don't know, like input-output libraries, linear algebra libraries, interfaces with Python or other languages. Yeah, you want something which is more modular. But I'm talking about performance, portability, and productivity, but do you need actually that kind of metric? Well, most of the time, probably yes, especially if, well, you want your code to run on different hardware technologies, like CPU, GPU today, but tomorrow you will have TPUs, like FPGAs, maybe after, like tomorrow or after QPU, quantum devices. Yeah. Also, if you have performance requirements, we do simulations in science that sometimes span over weeks or months of executions. And we want to improve. If we can gain 1% of efficiency, that means like a couple of days saved. Also, if you cannot afford to maintain and optimize different versions of your code for each possible hardware on the market, you don't want to do this kind of very technical job, which is far away from the physics and the science that you're doing. Because yeah, we want to focus on algorithms, on science, on the core idea, on the core stuff that our program is supposed to do. Not, I don't know, mangling with memory pools or stuff like that. We want to use them, but we don't want to develop something that does that. And also performance, portability, and productivity is important if you want your code to be easily maintainable and readable not by yourself, but by others, and especially non-experts like interns. So many of you are very young here, but think about the future interns or new PhD students that will work on your project. It's better if they can have something more in the portable productivity and portability mindset. But it's not always necessary to use those metrics, especially like if you need to tune your algorithms to work as fast as possible on a given hardware. Think about people who do onboard computation. Like you make a program that will run on a probe or on a satellite. You know that your program will run on only one hardware. So you don't need to make it like super versatile and use a library which is super versatile because you know exactly where it's going to run. And also if you want to explore a new architecture, because you may think that, yeah, if you want something which is flexible, a library which is flexible to work on different hardware, it takes time to obtain this kind of interface. And if you want to explore brand new cutting edge, sometimes even prototype hardware, you cannot wait. You want to use this with the API of the manufacturer right now. So I was talking about the programming model. So here is a raw attempt. It's more qualitative than quantitative to also, okay, this is more GPU, but bear with me, to play the different GPU programming models on this kind of ternary diagram of performance, portability, and productivity. Again, this is just very qualitative. You have, I know it's not the day for GPU, but well, this explains, this is more clear with GPU technologies. So you have more on the performance side, programming models like CUDA or HIP, which runs respectively on only NVIDIA or AMD hardware. On the other hand of the spectrum, you have directive libraries like OpenACC and OpenMP, especially OpenMP Target, that are more tailored for portability and productivity, but less on performance. But what I wanted to mention before, like you pick two of performance, portability, and productivity, and there is one that is a bit left behind. The idea of Kokkos, and also SYCL, is to be a bit more balanced, to try to be not bad in any of the three categories. So that's the main idea of it. So yeah, what is Kokkos eventually? So Kokkos is a performance portability and productivity parallel programming model, which is built on top of C++20 and is designed to abstract already existing parallel programming models. So in this graph, here you have the source of your application. You also saw the application is based on Kokkos headers, and the Kokkos, let's say, the core is based on existing technologies like OpenMP, CUDA, heap, and SYCL. So basically, we don't reinvent. Kokkos doesn't reinvent technologies to run on specific hardware, but it uses what is the state of the art of the different hardware. So yeah, Kokkos provides you data structures and functions based on modern C++ to build your application. And in exchange, you don't have to write low-level code. When I say low-level, it is something very close to the hardware or to the dedicated API to this hardware. Like when you use Kokkos, you don't write CUDA kernels by yourself. You don't use CUDA functions by yourself. You don't use OpenMP pragmas by yourself. You leave that to Kokkos eventually. One thing to mention about the Kokkos parallelism scope, Kokkos is designed to handle node-level parallelism, which is everything that happens in one node. And you need something else if you want to run it on a distributed memory parallelism. By instance, if you want to run on several nodes, then Kokkos cannot do anything for you. You need something like MPI, or I will mention it later, Kokkos.com, by instance, to achieve that. But if you have like several GPUs on the same node, yeah, it's fine. And it's on the same node, Kokkos can handle that. So what Kokkos provides you eventually? First, it provides basic capabilities. First, abstractions of the most used parallel patterns that we have in HPC applications, like loops, reductions, scans. It also offers an abstraction of basic data structures that we use in science, so structures of data for like vectors, matrices, or in other words, multidimensional containers. And well, you know, in Fortran, multidimensional containers, multidimensional arrays is something that comes with the standard of the language, but in C++, it's a different story. It also offers subarrays, trident arrays, etc. So all the interesting data structure that we need in our everyday developers' life. It also provides advanced capabilities, so the possibility to manage the data structure properties in a more advanced way, like layout, like data locality. It also offers thread safety, thread scalability, and atomic operations. And it also offers possibility to perform hierarchical patterns of parallelism in order to maximize the parallelism. But this is Kokkos core alone. Kokkos doesn't come with just the core features. It's also part of an entire ecosystem, which are other projects in the Kokkos galaxy. By instance, you have profiling, tuning, and debugging tools, which are covered by the Kokkos tools project. You have interfaces in Python and Fortran with PyKokkos and Kokkos Fortran entropy libraries. You have also possibilities to do linear algebra with Kokkos kernels, to perform fast Fourier transformations, aka FFT with Kokkos FFT, and to go beyond the limitation of the single node restriction of Kokkos with Kokkos.com, so that allows you to do distributed memory parallelism. So to call either MPI or Nickel to perform distributed computations. Eventually, all what I mentioned can be presented in this graph. So at the very bottom, you have you have Kokkos, the core of Kokkos, and even on the bottom, which is not on the graph, you have the actual technology that Kokkos is based on, so OpenMP, CUDA, AMD, etc. A bit on top of that, you have like the libraries developed on top of Kokkos core, which is part of the Kokkos ecosystem, so Kokkos kernels, Kokkos FFT, Kokkos.com, PyCokkos, Kokkos Resilience. You also have like resource, like Kokkos tools to help for debugging, profiling, etc., and resources, documentation, tutorials, trainings, online support, etc., etc. And then on top of that, so on top of the Kokkos ecosystem, you can have like libraries which gives you numerical algorithms, for instance, like Trininos, PETC, ArborX, DDC, and eventually on top of all of that, you will build your application. So your application can use Kokkos core directly, that's fine. You will use it. You can also use the Kokkos libraries of the Kokkos ecosystem, or you can also use the extra libraries that are built also on top of that. Eventually, I think it's a good opportunity to talk about the relationship between Kokkos and the C++ standard. So we have two people of the core developers of Kokkos who are members of the ISO C++ board, and they propose new features to the C++ standards. But in the same time, they also implement those new features in Kokkos using the existing standard as a proof of concept, and also as a testing playground to say, okay, we think it's a good idea, we try to use it with our users and get feedback. Is it efficient? Does it serve the goal that it has? And eventually, that can be used as the backport, like when this feature is integrated to, or if it is integrated in the C++ standard, the Kokkos implementation can be a backport for people that cannot use this standard right now. And you may think, okay, this is nice and dandy, but okay, practically, what does it mean? By instance, as I said before, multi-dimensional data containers is something normal in Fortran, part of the standard, but in C++ it's a different story. For a long time, it was up to the user to find a way to do multi-dimensional arrays in C++. Eventually, Kokkos proposed the MD-span. I won't talk about MD-span that much, but it's an ability to have multi-dimensional containers in C++. It was first implemented in Kokkos, and then it made it to the standard, and it is available in the C++ standard 2023. And Kokkos provided the reference implementation for that. So yeah, that kind of interaction, that's what I'm talking about. So Kokkos was initially a project developed in American laboratories that started in 2011. Back in the time, it was integrated to Trininos. Then it became its own project. Since 2023, it became part of the High Performance Software Foundation, the HPSF, which is part of the Linux Foundation. And this to make it not a purely American project anymore, and to guarantee the sustainability of the project for the long run, especially in the light of, well, modern developments with the American administration that gives more, say, security, especially as European users, but using this library. So here you have the list of the main institutions that are contributing to Kokkos. Most of them are American, obviously. So Sandia and Oak Ridge and Argonne, if I'm not wrong, were the main instigators, especially Sandia. And you see that CEA joined the board, CSCS, which is in Switzerland, joined the board also. So yeah, it's a joint effort to improve this library. Talking about CEA, I want to give a word about CEXA. So CEXA means computing at exascale with accelerators at CEA. This is an initiative that started in 2010-23 in the idea, in the light of the next Alice Recoq exascale supercomputer that will be made available at CEA in 2027. So the CEXA project is a joint effort at CEA to help the migration of HPC codes to GPU, using three means. By providing a GPU programming models, which is supporting Kokkos and entering in the development of Kokkos, by supporting application demonstrators. So we have what we name demonstrators are HPC codes at CEA that wanted to be precursors and wanted to use Kokkos to try and say, okay, how it's gonna work integrating Kokkos to our code base. And CEXA gives them support about this migration. If there is some specific developments to do in Kokkos, then CEXA will operate. And third access, by proposing dissemination of information, so doing trainings, meetings, and this is the really reason why I am with my colleague. We are here today to talk about Kokkos. There are some questions in the chat. No. Oh yeah, so with my colleague Thomas, we're gonna talk, we will present alternatively today. And so Thomas will take the questions when I'm speaking, and Sodier will take the question when he's speaking. That's good. Yeah, so in the chat, questions to teachers. Yeah, so feel free to ask questions there, and we'll try our best to answer to them. Is there anything, any questions? Good, okay. So yeah, don't hesitate, also in the room, you can directly ask. Don't go through the chat if you are here usually, but yeah. So here you have a couple of useful resources. So Kokkos is an open source project which is hosted on GitHub. So github.com/Kokkos, and we have all the Kokkos projects listed here. The documentation is on the kokkos.org website. There is a Slack channel for discussion with the devs, kokkosteam.slack.com, and there is a cheat sheet that at CEXA we are updated, so in the CEXA-project.org. So Kokkos right now is available on version 5.1.1, but the version 5.2 will be released this July, and it contains, well, interesting improvements. So I wanted you guys to have it for today, but it's a bit, well, too early. But yeah, at the end of July, you will have the new version. I think we are good. I don't know if I'm good on the schedule. Okay, sounds yes. I would like to give you a brief tour of the Docker images. So we try to craft them very carefully. My colleague, especially Thomas, was responsible of crafting them. So we propose images for CPU and GPU in 4 flavors with no editor. So you use whatever you want. It's not included in the image. With a Jupyter notebook, with VS Code, and with a learning platform code server. Both images are available in x86 architecture and ARM architectures, CPU, GPU. And what the image provides, so for CPU and GPU, you have Kokkos, the sources of Kokkos 5.1.1 and Kokkos tools sources available. You have GCC version 14.3, HDF5 for storing the results of the simulation, version 1.14, CLI 11 for the command line interface 2.6, CMake 3.31, and obviously the exercise folder. And when next week we move to GPU, you will use CUDA 12.8 and Inside Systems 2025 version. Okay, so I would like to make you work right now by first preparing the ground, because we will have several exercises today. They will take place in the Docker images. So here, I would like you to follow those steps. So you pick the image you want, either without editor or with Jupyter, VS Code, or code server. If you use Aptainer, you pull the image to have it locally on your disk, to have the CIF file on the disk. And you reserve a job for, I don't know, half a day of the full day, depending on the policy in your satellite site. And then when you are in, you run the image. Is it large enough, the size? Yeah. Maybe use them.
Is it possible to put this in the chat so we can just copy paste?
That's a great idea. Now, how can I do that? That's not a... Thomas, can you handle that? So yeah. So you may use, well, here are the instructions for Aptainer. You may use something else, Podman or I don't know. In this case, well, ask with the mentors if they are, depending on your satellite. Here, what do they use here? Aptainer or what do they use? Obtainer, okay, so normally you just have to follow just those instructions. And yeah, be careful. You won't have that much difference, but be careful to take the latest tag of the image. So there is only one tag, but that makes a difference. C'est bon? Okay, so normally, yeah, my colleague Thomas just posted those instructions in the chat. So you can just copy paste it and that should be good. For the demonstration, we will just ourselves, because we do also live demonstration of the work, we will just take the image without editor and we just edit the image, edit the files outside of the container. Do we have any difficulties in the room? Yeah. I see people typing on their keyboard phonetically. Good omen. Est-ce que je peux faire ça? Oui, je peux. I'm just displaying the. Okay, great. Online people, I mean, yeah, you can completely do this if you have access. I mean, what online? You mean not on satellite? I mean, you can do this on your own computer. If Obtainer is something you can easily install with apt if you're on Linux or your favorite package manager. Yeah, if you don't have access to a computer that can run Obtainer, yeah, but you can. Yeah, you can stick with the live demonstrations. Now you can definitely run it on your laptop. For today, we're doing CPU. So next week we will gonna use a GPU. So if you have a GPU, it's even better. If you don't have, you will be a bit stuck. But today it's just CPU, so you can perfectly do it on your computer. It works. Now the good thing about the container, it contains all the dependencies that you need for today. Yeah, I will explain the CP. Yeah, it's not on the screen. When you get in the image, I will explain the CP thingy, the copy the sources. So yeah, you need to make a reservation for the cluster that you're using. So we told Ratagosh, I will appreciate an official list of tutorials that can be followed on a reasonable good laptop. For today, you can even run it on a potato, it's fine. Because most of the development, we're gonna do it on a very small Grace code problem of 10 by 10, which can run anywhere. When we do performance tests, yeah, maybe something more beefy would be better, but at least for doing Kokkos today and with the exercise, it's fine. But yeah. Having a list of the tutorials, yeah, that would be good. So yeah, my laptop is an AMD GPU. Too bad. I'm sorry, because we only provide the NVIDIA images at least for this year. Next year, maybe. But yeah, for today, don't worry about GPU. It's just CPU, so it should run anywhere. Is it good here in the room? Don't be shy. Okay, I think I can explain the CP part. So Obtainer, what it does, it's when you run it, it automatically mounts the directory you are in the container when it's running. So you can communicate to the file system of your host. And since the work you are doing today for CPU, I would like to reuse it next week on GPU. So if I ask you to edit the files within the container, since we're gonna switch containers next week, your work will be inside the container. So here, what I want you to do is to copy the the pointer is even better, to copy the directory /home/jovian/examples to somewhere in your host file system. But install $home/Kokkos. And we're gonna work on this directory, which is not in the container now. Yeah, we will work on this directory. Like we will install, etc., build, and we're gonna do all of that in this directory. And eventually, when you are done copying, which is very fast, you just cd on that directory and go to the exercise directory where you have the folders of the different exercises for today. That should be good. Any difficulties? Don't hesitate to raise your hand if there is something unclear. Otherwise, I will just continue. Yeah.
Do we need to copy anything if we are on
Maybe the mic. So it's.
do we need to copy anything if we're on the must server?
Oh well, I don't know about this. Sorry. Are we good? Okay, so I'm move on. So let's investigate the sequential implementation first, because when you want, we're going to do this teaching with the idea that you have an application which is sequential and you want to Kokkosify it, to make it run with Kokkos. So we're going to start with the sequential implementation, which is in the exercise folder. So wait, I didn't do it myself. I should do it right now. So I'm on the Ruche supercomputer, which is hosted. Ah, yeah, right. Yeah, but I don't use the same. No, on this one. Why can I do that? Well, you don't have a good enough eyes? How can I? Oh, yeah. Better. Are you good enough? Yeah, okay. Okay, so yeah, I'm here. So I can just do. I have my cheat sheets to make it run. Okay, so I'm inside the image. So my fancy prompts tell me that I am in the Kokkos CPU Interactive latest image. And I will do the copy of the /home Giovan exercises to actually, since I'm in this directory which is mounted, I will just copy it here. Okay. Okay, so, and I go to the exercise directory, and this is what you have. Okay. Okay, let's go to the sequential implementation. I will would like to describe a bit what's going on here. So maybe not, I'm going to use my second tab. So yeah, this tab is not on the container when this tab is, and since they share the file system, so what I modified, I have it here. It's got Kokkos, exercise, and sequential. So I can use my own editor here. Okay, opening. Okay, so we will just going through the sequential implementation very quick. So we do some imports at the beginning. We have some specific headers of the projects. We'll just describe them if we need them. Here we define what is our real type, since we are using floating point variables. By default, we use double precision. If you want to experiment with single precision or something, maybe half precision, you can do it here. So every time we need a floating point variable, we use the real data type. With some constants, so that we picked from David Chamon implementation in SYCL, which is said to give good results. And I will go directly at the end of the file to the main. function where everything takes place. So yeah, we define some parameters, okay, to do the command line interface. We pass the arguments that we provided to the program, and we extract some parameters from it. Maybe I can. No. Can go to the header of parameters. So we have the number of rows for our problem, the number of columns. By default, it's 10. So it's very small simulation. The number of iterations, 100. The number of image intervals, so how many iterations, intervals before we write an image on disk, a snapshot of the simulation. This is automatic. And yeah, if we want to display the fields on screens, which is useful for debugging, and if we want to write the files on the disk. Okay, this is, and you get everything in the parameters struct, and you access the elements of parameters freely. Okay, so we create an array for U, an array for V. So we are in plain C++. We don't have multidimensional containers. We don't use MDSpan because it's C++ 23 and it's a bit too early, too new for our setup. So what we do the good old system. We create a one-dimensional plain old data array that contains the product of the rows and columns with extension because we have ghost cells on the outside of the domain. Okay. Here we have the output reader, which is the class to write the HDF5 file on disk. We won't go into details because it's not the point of today, but yeah, we create it and it's gonna create a grayscott.h5 file that contains the snapshots of our simulation. We initialize the U and V fields, U to 1 and V to 0, okay, for the entire domain. We add a drop, so we initialize the simulation. So this is a function which is provided in the file. We're gonna jump to its definition. So drop just creates in the tool cells at the center of the domain. So for U, it's gonna put 0, and for V, it's gonna put 1. So you have the U is initialized to 1, and you have a bit of 0 inside, and V is initialized to 0, and you put a little bit of 1 inside. Fair enough. You can print the field at the beginning, so normally you should have here for you like all the zeros and just 1 and vice versa, okay? We write the first initialization step to the disk, okay? And since the resolution of the Gray-Scott equation uses a Jacobi process, we create temporary arrays, utemp and vtemp, which are just as U and V, but with a different name. And we enter the time loop. So the time loop, we go for the number of iterations that we requested. Okay, we follow the, oops. Yeah, we go up to a number of iterations. And we call a compute function, which is where actually the main, say the resolution of the Gray-Scott equation takes place. So I'm gonna jump to the definition of compute. So compute takes the field U and V and the temporary fields U and V and also the size of the problem. So what's going on here? We have, since the problem is two-dimensional, we have two for loops, embedded for loops, one on the rows and one for the columns, okay? We perform the stencil computation. So I saw that the normal implementation is to use for loops for the stencil. Here we decided to just unroll the stencil, which is a bit more practical. You see that I have some like cryptic clang format off and clang format on comments, which is because we use clang format to format the code automatically to make things aligned and readable. But since this part is a bit more custom, then I asked the formatter to not operate here. That allows me to, display the line however I want, and this way I can showcase the stencil computation. So we use if I remember the weight pretty stencil. which is maybe the most correct one, but well, for 2 days it will do. We just want to focus on the computation. And you see that I use an access macro here, because remember, UNV are one-dimensional, but our problem is two-dimensional. So what we do is we have a macro that does actually the mapping between the two-dimensional and the one-dimensional data. And it's very simple, access that takes A and J, and that gives you the one-dimensional mapping of the, that we want to access. Is it clear? Any question about this? So it's a macro, it's very dirty, actually. It works and it makes the code readable. And I won't go into too much detail about the rest of the computation because I think this is very standard. We use the constant that we have in the constant namespace, and we continue computing things up to the point we have the new version of U and V that we store in utemp and vtemp. And same, we access multidimensional data within the access macro. Fair enough. I go back to the time loop. And then we do two swapping. So since U and V are pointers to data in the memory, we can just swap the value of the pointers in order to reverse U and V, in order to exchange U and V. And this way, this costs nothing. And compared to copying the new value of U in the old in the array U, it's much more efficient. It's much more quick because we don't copy our data. We just write a pointer. We just exchange two pointers. And at the end of the iteration computation, we check if we need to write the solution on disk, then we write it on disk. Fair enough. At the end of the computation, so here at this point, we have exited the time loop. We perform something that's going to be a bit artificial, but super convenient for us. We compute a checksum of our arrays for U and V. The checksum is very basic. We just add all the values in the array. And this way, it gives us an idea of what is the content of our arrays at the end of the simulation. And if we change the implementation, and if we didn't do any mistake in our implementation, the checksum should be the same, right? And if it's different, that means something went wrong. So it's like a word. I'm not sure it's something that real-world application have, but for today, it's a good helper for today's session. And eventually, at the end, you can ask to print the fields on the screen. Okay, and at the end, because we are well-educated C++ programmer, right, we free all the memory that we have used, especially the arrays. I see the people from Fortran smiling over there. But this is classic C++. Okay, this is there is no Kokkos involved here. This is just classic C++. Yeah, so what we're going to do is just build the code and run it. So I can keep the window open here. I go in the container here. So I will call CMake. So if you are not very familiar with CMake, oh yeah, I forgot one part. We use CMake for the compilation. So let's have a look at the CMake list that we are using. It's very simple, okay? You will see, okay, ignore this line. We include dependencies and common.cmake, which are, well, since we share, the different exercises share the same dependencies and common files, so this is a way to not duplicate things everywhere. But if you go to the, like dependencies, by instance, dependencies file, you see that, I will explain a bit more after, but like we try to find Kokkos, we trying to find HDF5, we trying to find CLI 11. Okay, we manage our dependencies like that. It is shared with the different exercises, so it just kept in one place. Okay, so let's try to compile this. So CMake-B to select the build directory, so where you're gonna put your product of compilation. Let's name the file just build build/serial. It will default for the source directory will default to the directory where you call CMake. So this one is fine. We want to do a production build. So you pass -d CMake build type equal to release. So this is standard CMake. Maybe it's a bit obscure, but the more you do CMake, the more it's going to be natural for you. And that's all, if I'm not wrong. Just configure. Okay, so it created a build serial directory. It doesn't contain much for now, but just the necessary to build the project. And we build CMake -- build and the directory where you have the build serial. Okay, you can even pass parallel if you want to perform a parallel build. Say we want 5. And it starts building. So the file system I'm using is a bit slow. We may have some access time on the demo. Yeah, okay, so we have in the build directory, we have Gray Scott. So I use CLI 11 for the command line interface, which means if I pass -h, I have my command line interface help message, and I can select with this the number of rows, the number of columns, the number of iterations, the interval between two saves, if I want to display the field on screen, if I want to not write, because by default I write the result to disk. Let's call it. Okay, so you know you don't need, as I said, it can run on a potato because 10 by 10 is just ridiculously small computation. The program gives you, go to the stop. It reminds you the parameters that you selected or were default selected for the simulation, okay? It gives you the amount of memory that we're gonna use for the 4 arrays that we have, which is ridiculously small. And you have, each time you write a file to disk, it tells it to you in the terminal, okay? And at the end, it displays the checksum that we get. So for the 10 by 10 case, the checksum for you after 100 iteration is 53.58, and for V, it is 0.60. So this is the value that we should have, we should keep as we continue porting the program to Kokkos. You can select a different, I don't know, like you want to do a 10 by 50 for the number of rows, it works. You see that I have 10 rows and 50 columns, okay? The checksum changed obviously because the shape of the problem is different. Yeah, and it's also outputted to us a grayscode.h5 file. So I won't be able to display it on screen, but HDF5 gives us some cool tools, F5, for instance, H5, what is the command already to display stuff? Dump. Okay, so it has dumped the file in ASCII on the screen, and our file that we just generated. But I'm just gonna rerun the simulation by just 10 by 10. That could be a bit more practicable. Okay, so this is not super pleasant. It would be better to have a graphical interface to display it as a, as a color field. But well, for debugging, that can be convenient. This is not super useful to use, okay, but since now we have a reference of the HDF5 solution, what we can do for the next implementation, when we start porting to Kokkos, is calling h5diff, which will take 2 HDF5 files and compare the content. That's going to be useful to check if we are outputted the same solutions. Do you have any questions so far for the sequential implementation? We are good? Okay. So let's go through the course because, well, what time is it? It's 9:49 and I haven't shown you any single line of Kokkos yet. So you're going to say, oh, well, it's a scam. So yeah, so let's start diving into Kokkos. Now we have the sequential implementation available. So Kokkos, as I said, is based on existing libraries that Kokkos uses through backends. So backends is the part of Kokkos that deals with OpenMP, with CUDA, with heap, whatever. Kokkos is compiled to target a specific backend. Okay, and your Kokkos application is portable until you compile it. When you compile it for a specific backend. You cannot select all the backends. Technically, well, there is a constraint that makes it not possible. You select one backend or two backends. I will give more explanation about it later. You have CPU and GPU backends. You need one compilation per backend. And the compilation is done through CMake. If you try to compile, imagine you get the source of Kokkos and you try to compile it and don't pass any specific arguments. By default, it will use the serial backend. The serial backend is just for serial sequential execution. It doesn't change that much anything compared to a sequential implementation. If you want to pass a specific compiler, for instance, you want to use the Intel compiler, so you're gonna use the normal CMake variables like -d CMake _ CXX _ compiler and give the name of the compiler. If you want, the name of the compiler is given in the table here. So by default, if you don't specify, you're gonna use GCC on Linux at least. If you want to use, I don't know, like Intel compiler, you pass ICPX. You want to use Clang, you pass Clang++, whatever. And you have the minimum version that this version of Kokkos supports, because there is a minimal version for the compiler that is supported. For GCC, it's 10.4, which is reasonably low. For Intel LVM, it's more recent, in 2024. You have more in the documentation, the online documentation of Kokkos, if you want to have more details about the minimum versions. So what you will do is just CMake configure for, and you pass all the options you want. So now we just keep the default, so we just pass the compiler. Even GCC is by the default, so I could even have skipped this line. I want to make a production build, so I pass CMake _ build _ type release. Okay. When the configuration is done, I compile. So in the build directory, I compile in parallel because we won't waste time here. And I CMake install, so I install Kokkos somewhere in the prefix path Kokkos, which is the directory where Kokkos will be installed. I will give more details about that. When you compile Kokkos for a specific CPU architecture, you can specify the microarchitecture you will use, okay? And you do that using the -Kokkos _ arch _ the name of the architecture = on flag. Be careful that Kokkos is written with uppercase K, but the rest is just lowercase. The architecture, it's something which is more important for GPU. For CPU, we pass it only when it's optional. It is only for optimization and especially vectorization. If you want to do vectorization, you have to pass the architecture. Kokkos won't auto-discover it by itself. You have more details in the doc, but here you have the most architecture flags, I mean, the most common you may have to use. When I say it's not automatic, I lied a little bit. You can pass Kokkos arch native = on, which auto-detect the architecture of your CPU. For instance, you run on a Skylake or a Cascade Lake, etc., it will auto-detect it for you. If you are an AMD Zen 5, you pass Kokkos arch Zen 5. If you are Intel Ice Lake, Arc ICX. If you are NVIDIA Grace, you can pass arch IMV9 Grace = on. Again, this is a bit cryptic, but when you go in the documentation, and I can go to documentation, because here we do sacrifices to show everything. So yeah, in the documentation, you have more details about the backend selection, okay, the options. There is some interesting debugging options, especially when you enable Kokkos when I should zoom a little bit, can I? We're gonna do that. Yeah, that should be good. By instance, there is a Kokkos enable debug bounds check. This is very useful. When you do a loops, you may sometimes go outside of the array. It means you ask the indices go outside of what the array contains, and sometimes it just can. But this is a mistake. But if by chance you go to you are staying in the memory of your program, you will have not an error. The program continues to work, but the result is obviously wrong. And when you enable debug bounds check, there is a check every time you access something in an array. Are the indices valid given the dimension, given the size of the array? And you're going to crash the program if not. But this is very costly when you do this check, because each time you access to memory cell, you perform this check. So that's something you do only for debug build, if you encounter problems or just to check, but you never enable that in production. All right, but most of the time, it's a good rule of thumb to just enable the Kokkos arch native equal on. There is one limitation to that. Imagine I am on a cluster, I am on a login node, and I build my program on the login node. But the CPU in my login node is different compared to the CPU on the compute node. And you're going to specialize, and if the two CPUs are different, you're going to specialize your build for the wrong CPU, and we just have seg fault when you start the program on the compute node. So be careful where you compile, where you execute. So yeah, as I said, Kokkos only use CMake. There is no make file to use Kokkos. That means that your project has to use CMake to use Kokkos and no make files. There are several ways to integrate Kokkos to your project. Here we just compile it. Well, you will just compile it and it's fine and dandy, but how in practice can I integrate Kokkos to my project? Well, the thing is, since we don't have a standard C++ package manager or dependency manager, there is many possibilities. You can build and install it, use Git submodules, use CMake fetch content, use Pack or other dependency managers, and unfortunately, none of them is the perfect solution. It a bit depends on what you want to do. And I would like to go through the different possibilities. If you just build and install, which is what we're going to do more or less today, you build Kokkos once, you install it somewhere, and you use it. Okay, it's great, because say you have 10 projects that use Kokkos, you just reuse the same installation of Kokkos, so you don't have to reinstall Kokkos again. Okay, that's the good point. But on the contrary, this is not very flexible. As I said, you have to compile Kokkos for each backend. So if you want to use several backends, that means you have to do several compilations and installations of Kokkos on your machine. If we want to enable the debug flags, for instance, you have to do this in a specific installation. If you have several versions of Kokkos, today is 5.2.1.1, tomorrow it's going to be 5.2, then you have to redo all the installations. So the combinatory of the possibilities starts to make a lot of installations you have to manage. And I find it very cumbersome. It's not dev-friendly. And also, the thing is, when you do that for your library, the burden of the installation of the dependency is on the user. So you make a library which is fantastic using Kokkos, and now, okay, now that's the user. Okay, now you do the installation yourself. I don't want to help you with that, which is not super convenient. There is a popular way of integrating Kokkos using Git submodules. So you may know Git submodules is the possibility to have one folder in your Git tree that is related to another Git repository. It points to it to a certain commit. So people do that. They have a specific folder, like the third-party libraries, and there is a Kokkos folder inside, which is a submodule. You get it by using a specific Git clone. I don't remember exactly the syntax, but Git clone, and you ask it to also fetch the submodules. And CMake, with CMake, just do add subdirectory to the Kokkos folder. So this is popular, but this, well, the first pitfall is that this command to clone the repository recursively. People usually, they they don't remember to do it, so they just git clone normally, so the Kokkos folder is empty, and then CMake complains that, yeah, I cannot find Kokkos. You will get a message which is not very related to the problem that you didn't also populate the submodules. And this is not very clean. And I give more details about what I mean by cleanness here. Another popular approach that I used to like a lot is using CMake fetch content. So you may know that CMake has an internal library named fetch content that allows you to download resources on the internet and put it in the build directory, especially source code. So you can just use fetch content to take a certain archive of the release of Kokkos, download it automatically, and build it along with your build. Well, it is very convenient, but if you want to do it right, it's not trivial. And again, it's not very clean. And what I mean by that is that, say, I made a library using Kokkos, and somebody wants to use my library. And in my library, I include Kokkos using git submodule or fetch content. But the library of the user probably also, I mean, he's using my library, he's also using, or they are using Kokkos as well. So what's gonna happen? My library uses Kokkos, their library uses my library and Kokkos. And if they include Kokkos the same way as I did, then CMake will have two inclusions of Kokkos, but not happening at the same time, separately. And eventually, this is gonna clash, because CMake will have twice all the targets of Kokkos. And CMake forbids to have twice the same targets. So it's gonna clash. It's named target clashing. So it doesn't scale. In other words, it doesn't scale. If you start using a real-world problem, a real-world application with many dependencies, and all the dependency depends on Kokkos, it's gonna fail. But it's very convenient, right? And for small projects, it's not too bad. It's very convenient. You don't have to set up something complicated. Then the last option is using an actual dependency manager, SPAC by instance, but you have other ones. SPAC is interesting because it's very tailored to HPC, and it contains many HPC libraries. So this is really good for production. You say, okay, my program depends on Kokkos version that, and there is this library that depends on so on Kokkos. And SPAC will find out, okay, you both want Kokkos, so I'm just gonna compile Kokkos once, find the version that is a common agreement between all the program that need Kokkos, and compile it once. SPAC is also good because it can bring the backend libraries for you. For instance, if you depend on CUDA and you don't have CUDA on the machine, which is not super likely, but it can install a version of CUDA. But the problem is, it's very powerful, but it's not trivial to use. And we haven't even written our first line of Kokkos that I'm telling you that you have to use CMake, and now that you have to use SPAC, well, maybe that's a bit too much to ask initially. However, if you have like half a day spare, I usually advise you to go through the SPAC tutorial, which is online, which is really good. And that gives you an idea of the powerful of that kind of program. Eventually, you may ask, okay, but which one I pick? For today, everything is installed in the container, which is very convenient, but kind of a little bit artificial. I would advise if you use small projects, you can stick with fetch content. But when you start to go to the real world and making real libraries, consider SPAC as an option. Okay, so for today, you will build Kokkos manually. So it's a bit like the first approach that we saw. The source of our Kokkos are included in the container, as I say, in the /src/Kokkos directory. So you're just gonna do this. You build wherever you want. Normally you are in, let me go to the, oops. You're in the exercise directory, so you can build stuff here or at a different level. It's not very important. Just remember where you put it, because you're gonna use the build directory for the actual building and for the installation. You build Kokkos without any option, so which means that we will have the serial backend with GCC, which is fine. This is what we want. you build in parallel, and you install it somewhere. Again, keep track of where you install. I suggest $home/opt/Kokkos/serial. It's up to you, but if you want just to keep the default, that's gonna be fine. Do we have questions? And in the room, do we have questions here? Ça parle? Ça dit quoi? Oui. So what's going on in the chat? Hey, chat. Can I close this? Okay, thank you, Tona, for copy-pasting the commands. So what about Pixie? We use Pixie, so Toma can give more insight about that. We used Pixie to install our build dependencies, so HDF5, GCC, and CLI 11. Can you install Kokkos with Pixie? The thing is, we need the source of Kokkos because we want to build Kokkos for a specific architecture. And as I said before, when you compile Kokkos, it's not portable anymore. It can only be run for the backend you want, and if you specify the architecture only for the architecture that you selected. So when you want to install Kokkos, well, there is no binary release of Kokkos because it doesn't make sense, especially for GPU. For CPU, can be questioned, can be discussed, but for GPU, it doesn't make sense. What do you recommend for installing HDF5 in the container? Well, we use Pixie. In my experience with containers, which is more for the web, when I have a container, I just use the default package manager of the container, of the distribution in the container to install whatever I want. And if I use Alpine, I just use pkg, install whatever. One thing you can do when you prepare your container, you can create your container and use pack inside to compile the dependencies you want. That's the way. It should be already present. I know, Thomas, that's you who answered. Yeah, HDF5 should be present. And when I build it, I didn't go to the details, but when I build the sequential implementation, I'm gonna skip all of that. So this is output. This is the output for the configuration when one configured the sequential implementation of the gray Scott equation. You see that in this line that CMake find HDF5, okay, and it gives even you which line it find, in which the shared library that it used, the version that it find, etc. Depending, that depends a bit on how the find the package for HDF5, it gives you, it prints you something, but you see that for CLI 11, it doesn't print you anything. Just silently, okay, it works. But it depends a bit. Alors, the CPU directory, so for now, don't touch the existing directories in the exercise folder because this is the different implementations. The CPU is the Kokkos CPU version of the code. If it's not clear, just shout in the chat or shout in the room. Yes, microphone.
Sorry, I may have missed something, but to build Kokkos here, you say that I wonder where is the source directory of Kokkos in the Docker, or maybe
it is in the image here. Let me.
I don't see it on my.
No, you're lying.
Okay. Or maybe probably.
/src. You
have
to be in the image.
Yes.
/src. You have Kokkos and Kokkos tools.
Okay.
And you have the sources.
Okay. I'll try. Thanks.
Okay. Does anyone find difficulties here? I'm just gonna do it with you guys. So, as I said, I cmake /s/soc Kokkos /b current folder build Kokkos serial. Okay, what do I need more? -d cmake build type. Release, that's enough. So we can have a look together. When you do the configuration, Kokkos prints some stuff in the output. It says, okay, this is Kokkos version 5.1.1. Okay. Okay, it generates some files in the process. And it says, okay, what did you ask? Built-in execution spaces. For device parallel, which is GPU, nothing was defined. That's right, because we don't want to run on GPU today. Host parallel, which is CPU parallelization, we didn't ask anything. And then host serial, yeah, we selected the serial backend. That's right. Architecture, I didn't want to specialize architecture. Maybe I want to enable the -d Kokkos Arch native equal on. And I do it, and this time, since I have enabled the Arch native, I have in architectures native. Okay. After, this is a bit internal stuff. So this is not very important. We can just build that, cmake --build, the build directory, Kokkos serial. Okay, parallel, say 20. I have 40 cores in this in the job. Okay, and when it's done compiling, I just cmake install. --install. The name of the build folder, build Kokkos serial, and where I want to install. So prefix, and I will just use the current directory. So I use $pwd. Sometimes it's better to cmake for installation folder, you give absolute directory rather than relative directories. So this way you are sure that it's going to be installed where you want. So pwd / I don't know, like install Kokkos /serial. And it copies all the file in this directory. And what we have, one can be curious. So now it's in the install folder. Install Kokkos serial, and you have the familiar build structure like bin for binaries, include for the include headers for the C++ headers, and lib for the libraries. You can, if you want to explore more, you can do it on yourself, but yeah, that's enough. Are we good? Can we move on to the next step from here? Any difficulties? What is it doing on the chat? Hey, chat. I mean, yeah, Arsalan, you can use if you're in the exam directory, I mean, if you mean the example directory, which is in /home Geovian examples, if you do that, you are inside the container, which is fine, but next week we're gonna reuse what we have compiled today. So that's why I would like you instead to copy the folder in the host folder and work from here. So you just use the container as the provider of your dependencies, but you don't modify the container. Tristan Guyon, yeah. The philosophy of CMake is that you never build in your source directory. That's something that Make used to do. And it's not a good idea if you want to have several builds. So the philosophy of CMake is that you create a build directory which is somewhere. It can be in your source tree, but it's a dedicated file. It's not the file of your sources. It's not the folder of your source. It's something different. And sometimes programmers, people who make the CMake list, they can enforce this distinction and make CMake to refuse to build if the build directory is in the same, is actually the source directory. So you specify the... You specify the build directory. I go back in time to show you what I did. Damn, it installs a lot of things. Yeah, I specify the source directory is -s, which is by default the current working directory, and the build directory is -b, capital B, and I put it different directory. If we are good, we can move to the next step. Now we have Kokkos built, which is fine. We can do our first step in Kokkos. What time is it? It's 10:16. Okay. So when you write a Kokkos program, you start from the very beginning. You include the headers, which is kokkos-core.hpp with capital K and capital C. Okay. So like any other library, you have to include the headers. Normally, you have only this header to include. Kokkos provides everything from this header. Sometimes you need a different header for specific stuff, which is a bit off the track. But usually with this one, you're good. And when you use Kokkos, when you call Kokkos features, Kokkos functions, classes, etc., they are all in the Kokkos namespace that starts with the capital K. So Kokkos, : and whatever the name of the function or class you want to use. A bit like MPI, for people who did MPI, you have to initialize and finalize your Kokkos environment. So you call Kokkos initialize at the very beginning. You can pass argument values, because Kokkos can analyze the command line and give you some, you can pass arguments to Kokkos directly. And you finalize at the very end. And in between, you have to create a scope with the curly braces. And this is where you will put all your code. And the reason for that is that when you call Kokkos finalize, this is especially true for GPU. For CPU, it's not that much important, but yeah, for GPU, it's more mandatory. When you call Kokkos finalize, there should not be any Kokkos object remaining live. So we use the scope in the way that everything that you define here, when we leave the scope, they get destroyed, and then you call finalize, and that works. If you prefer, if you are more like a C++ guy or girl, you could use the resource acquisition is initialization pattern. So you use the scope guard object, which is a very simple class that calls initialize in the constructor and finalize in the destructor. So you don't need to put the scope. And since, well, that should be one of the first things that you declare in your program, the other objects will be destroyed in reverse order. That means that at the end of the execution, you call the finalize after all the other destructors have been called. I prefer this way because it's a bit more compact. It's a matter of taste. If you want to go the classical, bit more C way or more C++ way, it's really up to you. It doesn't make a difference. We will just use a simple hello world, and I think it's a good opportunity to talk about the Kokkos printf function. The printf function works, well, it's designed to print stuff on screen, okay, and not on the printer like it used to be. It works like the std_print function, which will be available in C++23, but with the syntax of the all C std_printf function. So with the % and the type of the value that you want to print. And why Kokkos bothers to provide you a print function? It's because it works everywhere, especially from GPU. You may know that it's not that simple to print something when you are in the GPU kernel, and it works. Okay, so let's imagine that we made a simple program with just a main function, a scope guard, and a hello world. Simple enough. And now we want to build that, right? We want to build this program. So we use CMake because, as I said, Kokkos uses CMake, and we're gonna write a CMake list file. So CMake, maybe you're not familiar, I will try to keep very simple. This is the minimal that you need to have a valid CMake list and compile your Kokkos program. CMake minimum required is to tell CMake, this is the minimal version of CMake that I need for this script. We want version 3.22 because, if I'm not wrong, this is the minimum version that Kokkos 5.1 supports. Project, you declare a CMake project, you name it whatever you want, and you enable C++ as a language. Because when you do that, CMake knows, okay, you are doing a project with C++, so I'm gonna fetch a C++ compiler. And I will not fetch for, I don't know, the C or the Fortran compiler, because obviously you don't need it here. You include Kokkos in the project using find package. This is a clean way in CMake to include stuff. Say, okay, I need HDF5, I need whatever, so I find package, whatever. And you put required, because if CMake fails to find Kokkos, you want it to crash, because there is no point continuing onward. You call a command named add executable, which creates a target. So proj will be a target in CMake terminology. That contains just the main.cpp or whatever CPP file you want. And you will link libraries to this target using the target link libraries. And you just, here we want to link it with Kokkos. So you put Kokkos in, well, this is a bit weird, but you use the Kokkos namespace, which is Kokkos with a capital K, like as we did in find package, colon, and Kokkos, which is the name of the target. So when you do that, CMake will ask the compiler to inject the include flags for the Kokkos headers, and when you build the -L flag to link with the Kokkos shared objects. Did I miss anything? That should be good. Well, what's the difference in here? Yeah, and when you, okay, so you have your CMake list, okay? And now, if you want to build your application that uses Kokkos, you use CMake, you invoke for the configuration CMake-B for the build directory you want, a different one. You can pass the C++ compiler, but again, we're just gonna use for this time GCC, so it's fine. And you have to tell CMake, or you told CMake before, okay, I need Kokkos, so find package Kokkos. But CMake at this point just know that, okay, you want Kokkos, but where to find Kokkos? You have to give CMake some direction where to find this library. So you do this with the -d Kokkos _ root argument. So be careful that Kokkos, capital K, is the same as the Kokkos you entered in the find package. Pay attention to the casing. And you put here the path to Kokkos, the path where you install Kokkos. It can also be an environment variable. If you export Kokkos _ root path, absolute path to the installation of Kokkos, it works also. CMake will use this variable, these environment variables instead. Yeah, when you build also, you want maybe to have the CMake build type release to make a release build, because each release makes a difference. And then you build with the build directory in parallel. Well, for this case, for the gray scotch, you don't need a parallel flag because you just have two files to build. And that I propose you to do it right now. In the exercise folder, you have a hello world folder that just contains the hello world code, very simple. And this is just the crash test to ensure that you install Kokkos correctly, that everything works, and that you are with a CPU backend, and etc., etc. So let me show you. We are in the exercise. I go to the exercise directory. It's here. You have the hello world. Okay. I can open it. Well, this is very similar. What I said before. If the file system is cooperative. Okay, just a main function, a scope guard, and a printf. Good enough. So for now, just build it. You can run it when it's built. How are things doing for the chats? People have specific architectures. Well, Luke Hermit, I think you are referring to the scope guard if exception happen. Yeah, well, it's a bit more complicated than that because since nobody catches the exception, even with the scope guard, the destructor is not called. Okay, see Guillaume Direx had a problem. The examples folder doesn't have the permission for you to edit. It maybe, yeah, okay, that should be fine. It depends sometimes. The cluster may have, may treat the container a bit differently. That's why if you just copy it and you put somewhere, you have the rights. That's better. Does it work for you in the room? Yes. Okay, just gonna do it for the sake of completion. So I'm in the source directory, cmake -b build serial. What did I put? cmake build type. And Kokkos roots. So I put the directory I had before. Okay, so what cmake does tell us, he found Kokkos, okay. He found that Kokkos was built with a serial backend, so it prompts us that and nothing more. So I can just cmake build serial. Well, no need for parallel here, because there is only one lone file. And I can run it, and it works. Okay, you may argue that there was a much simpler way to just print the hello world, but well. And what's something you can do? I said that Kokkos initialize, it takes arguments, the input arguments, so you can pass Kokkos command lines arguments. So by instance, this my script, I had -- help. Okay, there is a bit more than I could have expected, because you have all the documentation from the Kokkos specific command line arguments. And if I add Kokkos twin configuration, it executes my program, but it also executes very useful function that gives me, okay, what is the configuration that you have? So I see that I built my program with Kokkos 5.11, okay. I use GNU compiler 14.3. I didn't select CPU architecture. Well, that's a bit weird. No GPU architecture. My platform is 64-bit. It's a bit weird because for architecture, I select Arch native, so a bit surprised that doesn't show up here. And after, it's a bit, well, obscure data, but here I have the confirmation that I used the serial backend. All right, so you have compiled your first Kokkos program. It was not that meaningful, but it's a start. Okay, so now let's go more in details with Kokkos and how to use Kokkos, because now we want to do meaningful things and not just a hello world. So Kokkos provides data containers. Is it good? I don't know. We are, yeah, okay. So we can have the break now. Maybe that's better. Before entering the main. Yeah, sure. So yeah, are we running late or? Okay. Ah, yeah, right. Okay, okay. So yeah, we have a 30 minutes break online and here. So we meet again at 11. Yeah. Okay. So see you next just after the break. Okay, welcome back, ladies and gentlemen. So I hope you enjoy your break, that you can have time to refresh yourself, especially with the heat that we are having now in Europe. We did our first time in Kokkos, and now it's time to dive in using the library to do what we actually want to do. So first, key concept in Kokkos is the data container. So how we put data, the data we are using. So we need an abstraction in Kokkos. So why is it important to have abstract data containers? The thing is, you remember in the sequential implementation, we did the allocation by hand with new and after delete, and that's something that, well, you don't really want to do this allocation and deallocation by hand every time. So you would like an object to do it for you automatically. Second, we want a unified semantic and portable way to do the memory management on CPU today and for GPU for next week. Because CPU, you saw it was just doing new and delete, but for GPU, but it's in CUDA, you would have to call CUDA malloc and CUDA delete, CUDA free. So it will depend on the GPU and the issue using CUDA or heap. So we want, in an abstraction, to have a single way to do the allocation and the deallocation. And everything which is vendor specific, so specific to CUDA, specific to heap, or specific to CPU, we don't want to have it on our code. And we also want an abstraction to provide advanced capabilities, like accessing to the layouts, subarrays, multidimensionality, etc. We also want to have safety through runtime or compile time check. That's something that Kokkos provides. For all of that, Kokkos provides the view class. So the view class is an abstraction of the notion of containers and multidimensional arrays. It provides you a container which the syntax and allows you to use it with a syntax which is close to Fortran or Python Numpy arrays. So you create a view. So view is a template class. You create it, so you use it from the Kokkos namespace, Kokkos : column, view, capital V, because it's a class. And it's, as I said, it's a templated class. So you pass template arguments. In C++, you pass the template arguments with the angle brackets. With that, you specify what kind of view, what kind of data the view holds. Here we want to make a view that contains single precision floating point variables. So we just put float. And you specify the dimension of the view. So how many dimensions this array should have. Kokkos allows you to go up to 7 dimensions. And you can specify the dimension either using a star, which means a bit like when you do an allocation in C++ or in C, that the size in this dimension is not known at compile time, but you have to specify it at runtime, or a bracket with a number of elements that says that you want, you know the dimension at compile time. And you can mix the two. Here, by instance, I create a view that contains floats and is dimension 1, and the dimension is only known at runtime. So when I call the constructor of the view, I pass the number of elements I want to have in it. And this value can be determined from, I don't know, the command line or something which is only known at runtime. Here I create a static view with a known number of elements at compile time. So I don't have to specify, I don't specify anymore the number of elements in the constructor. And I can mix the two. Here I create a view of doubles, of double precision floating points variables. With 2 dimensions. The first one is only known at runtime, and the second dimension is known at compile time. So when I specify in the constructor, I specify the size of the first dimension. And you can go on and on. There is a limitation due to C++ that you have to provide the runtime dimensions before the compile time dimensions. Most of the time, to be honest, you need just runtime values. It's fine. Oops, I should start a timer because we're already a bit short on time, and I don't want to make more mess than that I did already. You also see that I put a name in the constructor of the view, so this is very useful. This is useful for debugging and profiling. it's a really good thing to first name, well, the variable that contains the view to have a meaningful name, but also a meaningful description, which can be sometimes just the name, just the same name as the variable. That will gonna be very helpful for this, and we're gonna show this next week. Kokkos under the hood does a lot of checks at compile time and runtime to check if what you are requesting in the view is meaningful. Can be out of bounds with the specific flag that debug flag we saw before, or to do same size operations. For instance, if you have two views of different size, you cannot make them equal because there is a problem, the dimension is not right. How do you access the data when you construct a view? Well, you access the data with the parenthesis operator. So here in the example, say we created a view which is a two-dimensional view of integers. Okay, we created them and we want to access them. Say we have a normal nested loop, then I use the parenthesis operator to give the indices, okay, and I affect value to it. You can also access to the raw pointer of the data of the view using the data method, but this is not recommended. You do that only for compatibility with old libraries function that don't know what Kokkos views are and just accept a raw pointer. The view is an object, so it provides you some methods that you can use to query the state of the view. Among them, you have rank that gives you the rank of the view, so how many dimensions you have in the view. Extent with the ID of the dimension gives you the number of elements for a certain dimension, and the dimension starts with 0, as it is common in C and C++. And size gives you the total number of elements for all dimensions that you have in the view. So, for instance, I created a view of dimension of rank 3, so when I query the rank is equal to 3. I put 10 in the first dimension, so when I want to know the extent of the first dimension, it is 10. And the cumulative number of elements, so 10 by 20 by 30 is 6,000, so the total number of elements I have in my view is, well, 6,000 elements. There are other methods, but they are not that, a bit more uncommon, and we not cover them in this talk. When you have multidimensional arrays, I think maybe you're not familiar with that, but multidimensional array is the view of the mind, because the memory actually that you have in your RAM memory, the RAM memory is linear, it's single dimensional. So we map two-dimensional or more dimensional arrays to a single dimensional memory space. And for that to go from one to the other, we need a mapping. And the mapping, well, you can have several kinds of mappings. Here, in this example, we have a two-dimensional array, okay? And let's imagine it starts, the first element is in the top left corner, okay? But then where goes the next element? It can be on the same column, or it can be in the same line. And that creates two different layouts. When it's stored in the next column, we name it column major, for 2D, but also for the dimensions, or Fortran order, because historically, this is how Fortran manage multidimensional data. It's also named layout left, because when you have the parentheses to access the element with the indices A and J, you see which is the one which moves faster compared to the other. And in the column major, it's the indice of the left that moves faster than the others. And reversely, if your next element is on the same line, we name it row major or C order, and also layout right, because in this situation, the rightmost index moves faster compared to the other. So Kokkos provides an abstraction of the data layout with template arguments. And by default, when you don't specify the layout, Kokkos will use a default value. And this default value depends on the backend you're using. If you're on a CPU backend, on a host backend, you're going to be layout right. And if you're on a GPU backend, you're going to use layout left. If you want to specify the layout, you pass it as a template argument to the view after the data type of the data you have in the view. Kokkos provide layout left, layout right, layout stride. Usually, that's the one you need. You can create your own layout, but that's more when you're an expert, and we're going to cover this today. the default are largely sufficient for the use that we're going to do. A bit more about the views. So the views allocate data, but this allocation only happens when explicitly specified. When you create a view, actually a view, say, contains the data, but you can duplicate the view, and you don't duplicate the data. You just, a bit like a shared pointer, if you are knowledgeable about shared pointers in C++. The view itself just contains metadata and the pointer of the data that it contains. And when you duplicate the view, you just duplicate the pointer and the metadata. So the space where you allocated the memory, we're going to have more details next week about that, and that's why now I'm just making big gestures. But the space where you allocate the data remains the same, it's not duplicated. That's why when you copy the view, okay, we name it, when you duplicate a view, so you pass it to a function by copy, you just do a shallow copy. You just copy the pointer and the metadata, which is just a small amount of bits. You don't pass the view by pointer like you do in C. You can also pass it by constant reference, which is a bit cleaner, but yeah. Each time you copy the view, there is a reference counter mechanism, because we want to know, Kokkos want to know, okay, how many views exist that point to this area of the memory. And when there is no objects anymore that point to this area of memory, that means that we can safely clean the memory at this place. But as long as there is somebody somewhere who needs to access this memory, then we shouldn't clean it. Is this clear for you? Yeah? Microphone?
So how it is different, the shallow copy is different than the pointers, like I'm having little, confusion here.
So the view contains the pointer. It hides it to you.
Okay.
Is it clear?
But again, then the shallow copy, if you change the data, then you also modify the original data, right?
I'm sorry.
So in shallow copy, if you in the shallow copy data, you change something, it also changes the original data.
Thomas, can you move this one?
Okay, can you hear me? So yeah, if you have two views that are referencing the same data, when you access the data from one view, you will modify the content of the other view because they are referencing the same underlying data.
Okay, so in that case, then the pointer is more faster than the shallow copy, right?
Sorry.
In that case, the I think pointers are more faster than the shallow copy.
Faster in what sense?
In performance.
When you copy
access, yeah.
No, accessing is the same. And you will need the view because it also represents the multidimensional container and will avoid the access we had in the example in the Grayscott sequential. The view will allow you to hide all of this.
Thank you.
That's really the notion of encapsulation. But the question you ask is actually a very interesting one, and I have a good quiz about that. Imagine that I create a two-dimensional view, okay, which runtime, first dimension is runtime defined, the second dimension is compile time defined, okay, A and B, okay, they don't necessarily have the same number of elements in the second dimension, and I create, and I say A is equal to B. And then I create a third view, which is named C, which is completely runtime defined for both dimensions. And C is created from B. Okay? So now, this is what I do. On A, at index 0 and 2, I assign 1. Then on B, at the same 0 and 2 indices, I assign 2. And on C, in same location 0 and 2, I assign 3. And now I print the value of A at this location. What is gonna give? People think it's gonna be 1. Raise your hand. Okay. In the chat, any idea about that? You can spam 1 in the chat if you think it's gonna be 1 that will be displayed from this code. Okay, nobody. What about 2? Do you think 2 gonna be printed in the output? Raise your hand if you think it's gonna be 2. There is no judgment here. Okay, you think, okay. And in the chat, well. Okay, so Arsalan thinks it's 2, okay. And now 3. Who thinks it's gonna be 3 that's gonna be printed in the chat? Yeah, okay. And in the chat, how is it doing? So Hassan thinks it's 2 or 3, okay. Luke thinks it's 3, okay. 3, no, 4, no, out. You go out. Okay. Many people think it's gonna be 3, and yeah, it's gonna be 3. Because as we said, the 3 views, actually, they share the same data. They have pointers that point to the same address in the memory. Why? Because, well, here we did A equal B. That means that the allocation of B is destroyed, and we just use, sorry, the allocation of A is destroyed, and we just use the allocation of B. Now we create C from B, so that means that C use the same address as B. So eventually you have 3 doors to the same house, 3 ways to access the same data. Clear? Okay. So with this in mind, I will ask you first real exercise of programming. You will, from the sequential implementation, start using Kokkos views instead of the plain old C data structures. Before that, I want you to do a bit of plumbing. So you will duplicate the sequential directory to a directory, you name whatever you want, but it's going to be our work base for this morning and afternoon. And inside this duplication, you move the CMake list, you replace the CMake list.txt by the one which is named sample. Because this one is a bit more tailored for the Kokkos version. And you also rename the grayscode sequential.cpp to grayscode. So I'm just going to do it with you. So here I move. I'm in the main directory. Okay, I have the sequential, so I just duplicate it. Let's name it my grayscode, my JS. Okay, I go to this directory. You can remove the build directory because it's different now. The build directory of before when we build the sequential implementation. Okay, can remove the grayscode HDF file that was created. Okay, and I rename cmakelist.txt.sample to cmakelist.txt. And I rename the grayscode sequential into just grayscode. Okay. And now from here, I open the file, and you can start working. Yeah, you will need to add, obviously, the Kokkos header, okay, and use the Kokkos views instead of the plain old data. So I advise you to, when you use several times the same view, you can do using view, which creates a new type based on the type of the view that you want. So when you create Kokkos view double, 2-dimension, that's a type, and you assign this type to the name of a variable. And then you modify the access. So you should ditch the macro, the access macro that we were using to do the multidimensional access from the plain old data, and use the parenthesis to just directly say my view and the indices. So I give you, how much do we have for that? Like 10 minutes? 5 minutes to do that? Do we have any questions in the... you have any questions, don't hesitate to ask either in the room or on the chat for the satellites. Be careful, as I mentioned, to duplicate the sequential folder and do those first steps just to give you a working tree. That's gonna be our working folder for this morning and afternoon. And then you start modifying the file to add the Kokkos views in the sequential implementation. So doing that, we gradually are moving from sequential to Kokkos program. Which file is shown in the slides? You mean from the PDF file is the Kokkos CPU. We are at slide 50. If you want to follow directly with the PDF file, so you can just copy paste. Did we copy paste the command in? Maybe I can do that. Sequential. Okay. Question from Luc. I thought MD array and MD span were prototyping in Kokkos, and that's why view instead of those features is C++ type. That's a good one. Yeah, and Thomas was quicker than I. So yeah, initially when Kokkos provided multidimensional arrays, they did their own implementation, which was not MD-span. From this, they made the MD-span proposal to the C++ ISO committee and made a reference implementation. Now, Kokkos use MD-span under the hood with the views. I don't have a slide to compare that, but if you compare create a multidimensional view with MD-span and create a multidimensional view in Kokkos, it's a bit more compact and simpler within just the Kokkos views. And also it keeps it compatible with existing program with Kokkos that just use the views. One also of the very important point in Kokkos is keeping back compatibility with previous version of programs written in Kokkos.
And yeah, to add a point on this, there is no reference counting semantic in MD-span. So you need another container that will keep track of the duration of the memory. So they don't keep track of the number of reference you have in MD-span.
So I'm gonna do it very quick. So we create a view, which is a Kokkos view. I forgot to include Kokkos. Kokkos core.hpp. So I create my view, which will be of type real. Dimension 2, because we want a two-dimensional array. Okay. This part won't change. Let's go in main. So what changes here? Obviously, the fields, we change them now. So we have a view. So view is the type that we just created at the beginning of the file. A view U, we just name it U, okay? And it contains the same dimension as before, but not coupled together, but separated with a comma. Okay. And we do the same for V. Just name it V, okay. When we want to access the views to initialize, well, we don't need the bracket operator, but the parenthesis operator. Okay. What did I say about the... Oh yeah, I forgot to mention. You just modify it in main and compute. So in add drop, we don't modify it. So we just, as before, want us to pass a row pointer. So we just u.data method that just gives the row pointer. That should be the same. The helpers, if I'm not wrong, the helpers, they take, I think they can handle both, but we're just gonna disable it for now. The writer, with same, we pass the row pointer. And for the views, for the temporary views, same game. We create temporary views based on the same dimension. Okay, and compute, now we have to change compute. Oops. Okay, so we don't take pointers. We take views instead. So here I'm passing the views by copy. I could use constant reference. That wouldn't change. It's a bit, tiny bit faster, because when you do by copy, you increase the reference counter, which is a blocking operation. I won't go too much in details. But when you just pass a reference, you skip this step. We keep, for now, the loop as it is. And instead of using the access, we just use the parenthesis operator plainly. Do this for U, do this for V. So you see that we start to make the code a bit easier to read, because all this access macro to access multidimensional data from a single dimensional container, now we don't need that. It's just that we have the values multidimensional, we access them multidimensionally. You may ask, why do I have to use the parenthesis operator? Like, why can I just do something like that? You could be tempted to do something like that. If I'm not wrong, in MATLAB, I think this is, or in Python, you use like the bracket operator for multidimensional stuff. The thing is, here, it won't happen when we think that will happen. The bracket operator in C++ for now takes only one argument. Cannot take more than one argument. And when you use the comma, then it's not the comma for separating the arguments. In C++, row comma like that is, I do the first operation before the comma, I ditch the outcome, and I do the next operation after. So eventually, if you do that, it's just like if you were doing this. I was just specifying J, which is not at all what you want. If I'm not wrong, in the C++ standard version, I'm not sure, 26, you can do brackets and comma. So in the future, that's something that will be possible. Can you confirm?
Yeah.
26 or?
I think they started deprecating the use of the comma in 2023,
Ouais.
and you will be able to use the bracket operator like this in 26
Okay.
with empty span.
But for now, for limitation of the language, we have to keep just using the parenthesis operator. So I'm continuing removing the brackets. I could have used a macro. And if you're familiar with your favorite editor with macros or doing that kind of replacement just in a search and replace fashion, that would be more, that would be wiser because I may miss some stuff here. Oops. Okay. Okay. And I just check that I don't have missing access macro. There is one in check, but that's okay. So the check function, as I said, is the one that does the checking. We won't modify it because we don't want to modify the code and also the stuff that checks that our simulation goes right. So I just keep it like that. And this is only in the initialization that I have that. Okay. So I go back to the main function. The swap, I don't need to change it because it's good. We swap the two views. That's fine. Writing the output on file. Then we just pass the data. I use data method to get the row pointer. And the checksum, again, data method. Okay, for now I just disabled the printing of the fields. And at the end, I don't need the delete functions, right? Because at the end of the scope, the view gonna be removed. Okay, the view gonna be destroyed. The reference counter of the views will be equal to 0. So Kokkos will automatically clean the memory, since there is no views anymore that need to access to it. So and this is the big improvement already, because one of the main pain in C++ and C is memory management. And the more we can automatize it, the better. Did you succeed in the room to do the modification, to use the views and make it compile and run? I see no big hand waving, so I guess it's still a work in progress. Or is it in the chats? Ah, okay. So for now, we are using C++ 20 for Kokkos. So maybe, I don't know, next major, possibly. How do I make my Vim this nice and smart? It's a secret. But you can find tutorials online for pimping your VMRC. Okay, let's give it a try. I'm not sure it's gonna work on the first try, but so re-evoking CMake like we did before. Let's see. Maybe I missed something, possibly. Oops. Should give the hand to my colleague very soon. Oh, damn, we tried to compile it and cannot find the Kokkos core HPP. Maybe there is something we are missing somewhere. So let's analyze the CMake list because it is obviously a CMake problem. And maybe we forgot to do something here. Well, since subtlety is my middle name, I put a big to-do on here. Well, what do you think is missing here? Microphone, but it's microphone is here. Can you get it?
To link with the Kokkos library?
Yeah, because I mean, which Kokkos core HPP are we talking about? So in the CMake list, Kokkos capital K, column, Kokkos. Doing it again. And, oops, typo. You see that I tried to find something, it didn't, it wasn't right. Okay, I have some problems. So given that it's usually templated, sometimes the error messages are dense. $139. Ah, all right. Oops. No. What line is it? Ah, yeah, okay, yeah, I forgot. Yeah, because it was a single. So I have to modify the initialization loop. But actually, I can be a bit smarter. Should I go for the smarter options? No, I'm just gonna do it normal way. And create a second for loop. Okay. Try to compile again. So far, so good. It did compile. Will it work? That's another story. We got a sec fault, but we have some helpful error message. So we are using U before initialization has been called. Oh yeah, because I forgot. Indeed, in my haste, I forgot to initialize, right? So I'm just gonna use the guard. So you see that there is we forgot something, and Kokkos is, say, well designed enough to say, okay, you forgot to do that. You created a view when you didn't initialize Kokkos. And we have something, and what is the same as the sequential implementation? Because again, this is our reference, right? So let's run the sequential Grace code, and at least we have the same checksum. So far, so good. We just modified the data structures. Nothing fancy, nothing parallel for now, but at least our code gradually is moving to Kokkos and still becoming the same. Well, is still behaving the same. Do we have questions from here? Is it clear for all of you guys and girls? The chats, do we have... So if you want the solution, but... so this is... Wait. Marcelana have an error. I will just talk about this. So the solution for now, the solution is for just this step. Well, I can maybe copy-paste the file that what we have for now. It's gonna be painful, but maybe we can. Okay, I will just copy it in the put it in the chat in a second because that's a bit large to do like that. Somebody is reporting, so this stack is when CMake cannot find Kokkos. So maybe you forgot to Kokkos roots. Pay attention that normally check this path. Normally you should have the Kokkos installed here. If you don't, if you install Kokkos in a different place, that may explain why CMake cannot find it. Yeah. So in the CMake list, don't forget that you need to link, well, to link to the Kokkos library. So line 24 of the CMake list. There may be a typo, yeah. Yeah. Okay, if there is no other questions in the room, we can move to the next, subviews. Oh, well, very quick now. Okay, maybe we can go back to it later. That's interesting, but this is not useful for right now. And we can give the floor to my colleague, Thomas, to discuss about the parallel loops, how we can change now. Now we have changed the data structure, so we can change the loops.
Yeah, you have the slides, so the subview part was a bonus. So if you have questions also on subviews, you can still answer, we can still answer the questions. So now you have modified your source to use the data containers from Kokkos. So you have access to multidimensional arrays, which is nicer to use than the raw access using the pointers we used to have. And the next question is how to make it parallel. So we have different algorithms in Kokkos to make it possible. And we will start with the basic one, the parallel loops. So we take this example. We will be focusing on this kind of loop. We identify in this kind of loop the loop pattern. So here we have a simple iteration pattern. We have different ones like the reduction or the scan. We will shortly mention them later. So we will call that the loop pattern, the fact that it is just a simple for loop. We have what we will call in Kokkos the execution policy. And it corresponds in this example to this part, the fact that we specify we want to iterate from 0 to n and by an increment 1 by 1. And we have the pattern, the execution policy, and the final term of vocabulary we will be calling the body of the loop a kernel. So this kind of kernel is quite simple. We are updating, let's say, an array A from 3 other arrays, B, C, and D, 1D arrays. So think of them as the views you have just used in the previous exercise. One thing to notice is that for this kind of loop, and to make it possible to use with Kokkos, we assume that there is no iteration order in the iterations of your loop. So it means that you do not make any assumption that the fact that you start from 0, then you will go to 1, then to 2, and up to n. Because some algorithms could take advantage of this iteration order. And there is no side effect apart from updating the internal arrays that we are using inside the loop body. So we focus on this kind of loop with these assumptions to make it possible to use in Kokkos. So if we would go to OpenMP, like we saw, or OpenACC in Fortran, we would add pragmas above the for loop. So we would specify that to the compiler that we want to use OpenMP and parallelize the for loop, and it would be the job of the compiler to make it possible using multiple threads to distribute the work of the different iterations between the threads. One problem is that this will only work for CPU. And as we will see next week, we will want to use it on GPU. And so if we want to use it on GPU, you would need to modify this pragma to use the, so you would need a simple modification for this kind of example to add another directive, the OpenMP target directive. But the idea is that you need to make some modification. And we find it problematic, and we would prefer to use another kind of approach using Kokkos and the so-called parallel for. So this looks like this, and using this parallel for, we will be able to, up to recompiling Kokkos, we will be able to run either on CPU or on GPU with the same source code without any more modification. So let's describe what parameters we pass to this function. So as we saw in the sequential for loop, parallel for is the loop pattern, so it corresponds to the sequential for loop we had in row C++. We pass as a first parameter a string that will be able for debugging or profiling, as we will see next week. We pass the execution policy, so this is the simplest execution policy we can pass to the parallel for, as just an integer that will tell the parallel for function to iterate from 0 to n excluded. And we pass a lambda. So a lambda is a function object in C++, as you would also find them in Python. So we create on the fly a new function that takes an integer I that will correspond to the iteration identifier that we had in the sequential for loop. And we recover the loop body we had in the sequential for loop, the kernel, and we have the same code inside the functor. We have this extra Kokkos lambda, so you may know the notation in C++ to generate a functor, a lambda. It's the square brackets. Here we prefer to use the Kokkos lambda, so it's a macro provided by Kokkos that will hide some difficulties when we will go to GPU. So we prefer you to start using it on CPU as it will be necessary on GPU. When we talk about lambdas, there is the notion of capture, because we start using variables inside the lambda. And so the question that arises is how they are captured. So these variables A, B, C, and D are coming from the environment of the lambda. And by default, so in C++ you have two choices. You can capture by copy or by reference. In the case of Kokkos, we enforce the fact to capture the variables by copy. Again, this is the reason is for to make it portable on GPU. So yeah, I already started this slide. You can, if you prefer, you can even name your lambda and give it, store it in a variable and pass it to the Kokkos parallel for. As I said, the integer I represents the current iteration loop. And that's all you need to know for now. So we saw the simplest execution policy passing an integer, a single integer that will let Kokkos generate n iterations starting from 0. But you may want more complex execution policies, and a more complex execution policy is just to start from some offset. If you don't want to start from 0, then you will need to create a new object from a class called range policy. It's a template class. And in this template class, you can specify where to execute the parallel for. It's called the execution space. For now, we can skip it. It will be necessary essentially for next week. And it takes 2 parameters. This range policy takes the first index of the iteration space and the end index. So yeah, note that the start index is inclusive, so you will get this index in your during the execution, but the end index is exclusive. You will not get it. So yeah, to compare it from the single integer case, you can even skip the execution space parameter. There is a default for that, a default value. You still need, in some cases, the angle brackets. And if you want to have the same semantic as the first version, if you want to start from 0, then you just specify 0 as the first parameter and n for the last index. So this handles 1D loops. But as we have in the Gray-Scott equation, we are facing nested loops. So in different places of the Gray-Scott equation, you have 2 loops in a row. And actually, Kokkos provides a specific pattern for this, for the nested loops. So if we have this example of I and j loops, where you update some array A, you can, in some cases, collapse them with, for example, in OpenMP, you have a specific clause to tell OpenMP to parallelize over the 2 loops at the same time. We assume, to make it compatible with Kokkos, that there is no dependencies between the two loops, I and j. And same assumptions as for the range policy, no iteration order and no side effect. Same assumptions. And if you want to let Kokkos know about this kind of pattern, you need to change the execution policy from range policy to MD range policy. So this is another class, which is also template, and where you need to specify the dimensionality, the rank of the loops you will be using. So yeah, it can go to up to 6. It's not infinity. You cannot go to 7 or 8. You will need to do some extra work by yourself if you want that. But in many cases, this is largely sufficient. As we have nested loops, we need to specify the start index and the end index for each of the loops. So you need to pass them. The first parameter corresponds to all start indices, and the second parameter corresponds to all end indices. So this is quite similar for the semantic of start and end from range compared to ND range. So as an example, we replaced here N or MD or range policy with the MD range policy. Passing here in this example, we want a 2D loop. So we pass, you must provide this class as a template parameter, specifying that you want a 2D loop. And we want to iterate from 0 to nx and 0 to ny for the second loop. And so you recover these parameters in the constructor of the class MD-range policy. One thing that changes also is the signature of the lambda. Instead of one index, of course, you will get two indices, I and j, two different parameters, and it's your work to use them in your body in the kernel. So this looks really similar to the range policy. And yeah, here in this case, there is no shortcut version, meaning that you cannot pass only nx and ny compared to the range policy where you could pass only n to have simple 1D range policy. Yes, a question?
Yes, excuse me. Oh. Does this work? Oh. How is the contiguity managed when you have two dimensions here?
Yeah, I think this is something we cover next week also. So we don't show here all the template parameters of MD range. You have extra template parameters where you can specify a preference on the iteration order between the loops, because you have the I loop and the J loop, and you may prefer to have the J loop first on the outer loop rather than the I loop. And this is controlled by a template parameter. So you don't need to change as if you had a sequential C implementation, you would have to have if-def or change your source code to make it to change the order of iteration. Here you just need to specify an extra template parameter. You can have it as an alias somewhere in your code to specify it. Of course, you also need to be careful of the layout of your data. So this is not only a question of MD range policy, it's also a question for the layout of your multidimensional container. And yeah, if you don't have more questions, we have an exercise, if we have time. 3 minutes, challenging. The idea is to use Kokkos parallel for in the gray scots where you find nested loops. Focus on the gray scot, the computation kernel. No need for now to care about initialization or extra loops like this. You can focus on the loops that apply the stencil. We know that we have nested loops in this kernel, so we want to use MD range policy. We have 2D loops, so an MD range with rank 2 should do the work. Yeah. Thank you. Comment ça se fait? So you can continue working in the same directory, my.js, as we called it. So sorry, I will start using Emacs. Yeah. So for today, you don't need to modify add drop. Actually, we didn't even modify for the Kokkos view. The idea is to replace these 2 loops. So this is actually quite straightforward. You call Kokkos parallel for MD range with an MD range policy. We specify that we want a rank 2 iteration. Oops. We need to pass the bounds of our iteration space. So the first parameter, as we saw, is the beginning of the 2 loops. So both loops start at 1, so we specify 1, 1. Oops. And the end. Oops. So for the first one, we have n rows next. So the difficulty is also the syntax of C++. We align a lot of parentheses and brackets and curly braces. So here at the end of the line, we should have constructed an ND range object. And the second parameter is the lambda. And then we can comment this. So these are for the 2 C loops. So the curly braces here ends the definition of the lambda, and the parenthesis ends the call for the Kokkos parallel for function, if I'm not mistaken. We can try to compile that. We can add a small string to identify the the loop we are executing. And if we recompile, does it work? Surprise. Okay. Did it change? So each time you make a change in your work tree, compare it to the checksum. And if I'm not mistaken, this is the same. The 53, yeah. So it worked. So we simply replace the 2 nested loops, the 2 C nested loops by a Kokkos parallel for. And that's all you need to do to make it Kokkos compatible. And as we will see in the afternoon, to make it parallel. Because even though we call the parallel for function, it also depends on the backend you compiled Kokkos. So for now, we made you compile. We didn't specify it, but it was a serial backend. So you don't have any parallelism yet. We will need to recompile it to have a parallel execution of this kernel. And that's all you need to do. Do we have questions regarding this change? Looking for the Discord. Ouais. Here. Yep. Do we have questions online? Yeah. Yeah, that's not me on the keyboard. That's you. So be careful. Be careful. Questions in the room? If not, we can meet in the afternoon. Okay.
Okay, so thank you everyone for attending this this series of lecture on exercise on Kokkos. We will continue a bit this afternoon, and then we will do some magics with precision with Vincent, as he mentioned yesterday. So have a great lunch, and see you at 1:30 for the scenery presentation at Senegal, and then we'll go back in Kokkos at 2.
of your video, Adam.
And
Okay.
you guys are live. I'll leave you the floor.
Okay,
Okay.
so welcome everyone for this fourth day of the Grace School. We now go live to one of our satellite sites, the Scenery in Senegal, where more than 80 participants are gathered. Record for this edition. I am pleased to hand over to Adama Koli, and to all of you listening, feel free to join the discussion and ask questions after the talk. So Adama, it's yours.
Okay. Thank you very much. And hello, everybody. I'm really pleased to attend to this session of Grayscale School edition of 2026. And it's really a pleasure to be with you for the third time as a satellite site. So my name is Adam Okoli. I'm the Director of High Performance Computing at Scenery, and I'm here to present you Scenery and supercomputer Tawwe, our supercomputer. So I will try to cover these steps, and I will talk about Scenery, and after that I will talk about our department, HPC department, and I will talk about some use cases used on the supercomputer, and for the end I will talk about users engagement, training, and community development. So Scenery stands for Cyberinfrastructure nationale pour l'enseignement supérieur, la recherche et l'innovation. It's a general directorate of the Ministry of Higher Education here in Senegal, responsible of research and innovation. And it's established under decree number 2021-1144. And Scenery serves as a Senegalese national cyber infrastructure for higher education, research and innovation with a mandate to provide and operate strategic digital infrastructures supporting education, research, and innovation nationwide. So the key responsibility of Scenery are to manage the Tawwe, the supercomputer, Senegalese national supercomputer, to manage the SNRS, which is the National Research and Education Network, connecting in universities between them and with us, the Higher Education Data Center, and also the CGS, which is the Integrated Governance Information System for Higher Education and Research. These infrastructure support scientific research, digital services, and data management and higher education governance at the national level. So for the HPC department, it is responsible for managing and developing national scientific computing capabilities, including the Tawwe supercomputer, which serve as a strategic infrastructure for research and innovation. Our mission is also to enable the full exploitation of data potential to support real-world application and use cases that contribute to sustainable socioeconomic development. We also play a key role in ensuring digital sovereignty and strengthening the national computing power and reducing dependency of external infrastructures. So finally, we are committed to promote and foster Senegalese innovation and provide advanced computational resource, supporting research and enabling the development of cutting-edge scientific and technology solutions. So the supercomputer we are using is named Tawwe, and Tawwe is referred to a river branch in Senegal that is essential for national water resource and reflects its role as a source of growth for research and innovation. It's operated within a high performance computing infrastructure. So it was acquired in December 2019 and official commissioning in March 2024. After its full deployment and integration into the national digital ecosystem with a peak of 537.6 teraflops. So Tawe ranks as the third most powerful supercomputer in Africa and reflects Senegal's growing capabilities in advanced scientific computing. So this infrastructure plays a key role in supporting research, innovation, and data-intensive application across multiple domains, including climate modeling, health, energy, and artificial intelligence. So the main component of the supercomputer Tawe are nodes separate on partition. So we have 3 partitions. We have the SYCL partition composed of 198 nodes with the processor Skylake, which have 18 cores, and we have also 36 nodes partition KNL, so night landing processors, and we also have 12 nodes partition for GPU, and the GPU we are using are NVIDIA V100, excuse me. So we also have a node which share memory for the users, which is SMP, and its capacity is 6 tera of RAM. We also have a Scratch of 1 petaoctet and a home directory for users of 10 terabytes. So for the interconnection, we use InfiniBand and Ethernet as a network interconnection for administrations. I'll present some use cases we are developing in Senegal. So the first use case is a simulation of pollution dispersion in critical maritime areas of Dakar. And the key outcomes are the identification of pollution dispersion patterns and hotspots. And we try to improve understanding of coastal ocean dynamic to support the environment decision-making and coastal protection policies. We work in this project with the University Amadou Mahtar Mbow, which is our main partner on this field. So the second use case is the scalable genomic analysis with nanopore and Illumina, so that we can have these outcomes to have a rapid processing of large-scale genomic datasets, reducing time for real sequencing analysis, improving accuracy and efficiency of bioinformatics pipelines, and scalable optimization of nanopore and Illumina workflows. So we work in this project too with the University of Dakar, which is Cheikh Anta Diop, and we work with a team of the FMPO. So for the last case, it's the urban floods modeling and risk assessment. And the key outcomes here is to make a realistic simulation of urban flooding scenarios to improve understanding of rainfalls, drainage, rainfalls, and drainage floods relationship to support the flood risk prediction and early warning systems. So this allows us to make some decision supports to urban planning and sanitation infrastructure. So in this work too, we are working with the University Amadou Mahtar Mbow and the Ministry of Water and Sanitation in Senegal, combining scientific modeling, computational infrastructure, and public policies expertise. So for the user engagement and training community development, the key achievement in 2026 for now is that we have users from many domains, including academia, research institution, and industry. And we have over 100 access requests received a year, and demonstrating a strong interest in HPC resources. We also have many active research projects currently running on the platform, and we also have many training sessions delivered to support users onboarding and capacity building. So for the Graduate School this year, so Graduate School is our main activity here since 2024, And CNRS has been selected as a satellite site for the Grayscale School since this year. And we have this year, as they said in the beginning, over 80 participants that registered through the Dakar site with just 30 trainees hosted directly at CNRS in Jamnad. This initiative has contributed to building national HPC expertise, fostering collaboration, and growing the community of research and engineers using advanced computing resources in Senegal. So for the impact, we are trying to build, with that, we are trying to build national expertise in scientific computing and data intensive research, increasing adoption of HPC technology across research and innovation sectors, developing a sustainable ecosystem of users capable of leveraging advancing computing resources for scientific and socio-economic impact. So that's all for my presentation. I want to thank you a lot and have a good day.
Thank you, Adama. Thank you very much. And we are always really pleased to have you as a partner for the Grayscale School. Yes, indeed. Now there's the room for questions. If you have any questions for Adama, it's now. So it can be in writing on the Discord, on the dedicated channel, or in Annecy if you have anyone.
Thanks for the presentation. You mentioned the Kokkos simulation during your presentation. This is something you collaborate with France for this, or this is about fluid simulation, or this is another code you are using on your side?
It's another code we are using on our side. It's with a lecturer, and we can be in contact to work with that. We use Kokkos to develop the model of simulation for polyon dispersion in critical maritime areas of Dakar. So you can just let me a message and we will talk about that next time. No problem.
Okay, thanks.
Okay, I guess that's all for me.
Yeah, checking no questions on Discord. If you have any question later, you can still use the dedicated channel.
Yeah.
Okay, so is there any question in Annecy?
So I just wanted to know that how much of scientific computing is going on in your HPC, like the percentage wise, like physics, chemistry, life science, and then maybe AI or social science. Do you have any data on that?
I don't have exact data on that, but of course we have many parts of scientific computing used here. And here I just present some parts of physics and medical and also environment, but we also have many demands on AI using of the HPC and also for the scientific data's reading. So that's why we cover many domains and we try to give our best to provide resources to the users so that they can use it greatly. I don't know if I addressed to your question well. I respond to your question well.
Okay, so I think if there's no other question, we can.
I think, yes, we're good here regarding the questions. Thank you, Adama. Thank you for your presentation.
Okay, thank you. So,
thank you, everyone. We will resume at 2 p.m. So let's have a little break. Hopefully the European heat wave will take a short break too. Let's have a little break and let's meet at 2. Okay, bye.
Okay, bye.
Thank you, guys. Bye.
Bye, Adama.
Okay, welcome back everybody for the next part of the Kokkos lecture on CPU. So we'll continue a bit of wizardry with that. And after that, we'll have a seminar with Vincent on the precision. So Thomas, it's up to you.
Thank you, Pierre. So welcome back to Kokkos on CPU. I will start with a reminder, a recap of what we did this morning. So we stopped at parallel loops. So we have seen the motivation of Kokkos, why Kokkos exists. We have seen the first Grace code implementation in serial that we started to port in Kokkos. So first, changing the containers using the Kokkos containers, the main one being the Kokkos view, so which roughly speaking is a multidimensional container, so an array, multidimensional array. And we ended this morning lecture by parallelizing the main loop, the main kernel, which applies the stencil, the Grace code stencil. So we only did that. Of course, there are other loops that we could do also. Like the part of the initialization could also be done like this. But we will continue with the parallel reductions. So another kind of algorithm that is present in Kokkos. So we did the anatomy of a for loop this morning. So now we do the anatomy of a reduction loop. So the main difference with for loop, the for loop pattern, is that in the case of the reduction, the iterations will have kind of a side effect on a variable that is the result of the reduction. So the idea is that there will be one, let's say, scalar variable that will collect something that is done at each iteration in the for loop. So it can be a sum, like in the example. So in this example, we have a double variable called result that is initialized to 0. And at each iteration, we contribute to result by doing a summation with the content of A of I. It could be, so this is a summation, but it could be a reduction over max, over a mean, and we have plenty others available. One side note is that contrary to the for loop, here the iteration order may have an impact on the result. So the result here is the reduction over the variable called the result. And depending on the way, on the order of your iterations, due to floating point precision and non-associativity, you can have slightly, or in a few rare cases, really different results. And yeah, this is a special case for the floating point arithmetic, or if we generalize to all non-associative reductions. A note is that for a max or a mean, you should not have this kind of problem. And a reduction over an integer, a summation for an integer result should not also have this kind of problem. So we want to have a look at the Kokkos version of this kind of parallel, of this kind of pattern. And it will look quite similar to the parallel for that we saw this morning. So it takes the form, again, of a free function in Kokkos. Something that that you may have noticed, but we didn't mention, is that all the symbols of Kokkos are in the namespace Kokkos. So you will not find parallel reduce without prefixing by Kokkos. So yeah, it takes the form of a free function called parallel reduce. It behaves similarly in terms of execution policy. So you have a second parameter that represents the execution policy. It takes again a lambda where you will do the work you want to parallelize, and that will be similar to the content of the previous for loop we just did. And so a difference in the lambda is that you take a second parameter. So you have the integer I that represents the current iteration. And the value, by the way, is provided by Kokkos. And you have a second parameter, which you must take by reference because you will have a side effect on this variable. And the side effect is written here. Slightly different from the previous slide. We contribute to local results with I. It could be A of I. It would be similar. And the thing that I want you to remember is that you should not, and actually I think you cannot, contribute directly to the global result. The idea is that this local result represents a result that is private to a thread that will execute the lambda. Then the threads will then assemble the results into the global result variable. And this assembling of the partial results is done by the final parameter, encoded in the final parameter, which is called the reducer. We have predefined reducers in Kokkos. Here we have a reducer called sum. And this is a class, a template class. And it takes the variable that will hold the final result as an input variable for the constructor. And this reducer encodes how to initialize private local results to the thread, and also provide the way to combine, to join between the results between the threads to make the final result. As it is noted, the local result is write only. So you can, of course, read the current value, but it is meaningless. You cannot rely on it. So you should not read the value. As I said, we have different predefined reducers in Kokkos. So I just shown the sum results. We have max and min, so that just combines the result you're doing the maximum and the minimum. We have the products and other useful reducers like the max lock and min lock. What we mean by that is that it will be a combined result between the maximum and the location of this maximum. It can be useful if you want to detect a phenomenon in your simulation and you want to know where the maximum appeared in your mesh or whatever. And so the max lock will have two variables encoded inside. Typically a double or floating point value, and an integer identifying the current iteration, the iteration that produced the maximum. And yeah, before answering a question, you can also create your own reducer. Not covered in this talk, but you can find documentation on the official documentation where you will have to define a class which instructs Kokkos how to join, how to do the initialization of the private local results. And that should be all. Yes, we have a question.
My question was, since the logic of the sum was implemented in the Lambda, does this mean that the reducer is just like a data transfer object, or does it implement it in a logic itself?
So you refer to the fact that we encode 2 times?
Yeah.
Yeah. This is due to the fact that internally Kokkos will have to assemble the partial results,
Okay.
and it cannot know what was your intent in the Lambda.
Okay.
It does not know what happens inside the Lambda. It's a black box for Kokkos.
Yeah.
It will just call the function with passing the current integer and the local results. But it cannot know whether you are here doing a max, a summation, or whatever. And so the need to pass an extra variable that encodes your reduction is to assemble the partial results.
Okay, and it gives a little bit more expressivity, so we know what you're doing inside the Lambda, right?
Yeah, exactly.
Yeah.
You are supposed to do the same kind of operation between the reducer you provide here and the content of your Lambda.
Okay, yeah, so if I put like a max there, it won't work, like Coco will try here, or...
Here, if you do a max,
Yeah.
and here you pass sum,
Yeah.
no, it will not know. It will produce a result, but completely undefined.
Okay, okay.
Yeah.
That gives me like another question that
Yeah.
I have. Suppose you said we shouldn't touch about the global result variable inside the Lambda.
Yeah.
Let's suppose I add, I don't know it. I add the Lambda, the result inside the Lambda. Will it like aggregate the result and explode with bigger sums, or will it just crash and throw an error? Because it can be used as a feature.
I think if you we saw this morning that the Kokkos Lambda captures by copy.
Yeah.
So it will capture a copy of result if you start using it inside.
Okay, so yeah.
And I think this operator. So this is the function call operator of an anonymous structure, and by default it is const. So you should have an error saying like you are modifying a variable in a const operator. You can do, but if you really want it, you could have nasty things like taking the pointer and dereferencing it inside the Lambda. I don't know the result. I'll let you try.
Yeah, we'll try it. Yeah. Thanks.
But clearly you are messing up with the semantic of Kokkos. It's not supposed to, you're not supposed to do that.
Okay. Thanks.
And yeah, if you start taking addresses or references of this variable, you will likely have an error when you compile for GPU because you are using a host variable inside a device region. These are different memory spaces. It should not work, even not compile. So yeah, you can create your own reducer. So you will need to provide the logic needed by Kokkos, the join and the init functions, and maybe other things. I'll let you see on the documentation if you need. So some examples. We start with a sum reduction, a more complete examples than before. So we have a result. Note that you don't need to initialize the result. We will overwrite the content of this variable. We declare a view. So we saw this morning that this represents one-dimensional because we have one star and representing double elements. It's supposed to be initialized, so constructed with a size and with meaningful values. And we want to do a sum reduction. So we call Kokkos parallel reduce. It's similar to the parallel for we can pass a string to help in debugging and profiling your application. Here we make the choice of passing a single integer, so the simplest execution policy we have. And we define a lambda, taking an integer I to represent the current iteration and the local result that needs to match the type of the values you are trying to reduce. We read the content of A and we aggregate the result to the value to the local results. And we pass only results in the location for the reducer. There is a default behavior in Kokkos where you can omit the class sum in the case of a summation, a reduction summation. This is the only case. If you want to do a product or a max, you need to pass a reducer. It will not work, and if you omit it, you will have this kind of error, as you asked, where you will do another reduction here, and while Kokkos will think you need a summation. A max reduction, so this is quite the same. The only difference appears in the lambda function and in the reducer. So instead of having plus equal here, you call a function from Kokkos, which is called max, that will return the maximum between a of I and the local value, and store the value in the local max in the local reducer. And of course here, we must, as I said, pass the kind of reduction we are doing, so this is a max. Be aware that could be an easy mistake. The Kokkos max function is similar to the max function you have in the standard library of C++. So it takes two values and returns the maximum between the two. It's just a portable way of max because it already exists in the standard library, but it will not be usable on GPU. So Kokkos provides a portable max function, and it is different from the reducer, which is the custom class of Kokkos, which encodes how to join and how to initialize the local reducers. These are really two different objects. An example of the minlock that we previously mentioned. So the minlock is slightly different. It has two template parameters because you need to say what is for a type representing the maximum and a type representing the location. So this is the reducer, but if you will need to know the type of the local value that will, the global value that will do the reduction. And if you don't know it, you can just retrieve it from the alias type inside the class that is called value type. So instead of, as in the previous example, having double for the global results, we have this minlock type that is taken from the minlock reducer. Same as before, we call parallel reduce, a string, the execution policy, a lambda. We pass, instead of having double here, we again pass the minlock type. And we have a bit more work to do in this case. We need to store the maximum value. So we have a contribution. So this type has two variables, a variable called val and a variable called log. And you need to contribute to both so that you can have the location of your maximum. And yeah, the value type is available for all reducers if you need, and it can be useful in generic programming. And I think this is the final example. You can also do multiple reductions at a time. And it is as simple as passing multiple reducers in the final arguments of the parallel reduce. So here we want to do, in this case, a sum and a min over an array A. So we pass sum, and so here we don't pass the Kokkos type reducer because Kokkos can infer it, because we only pass the scalar. And in the case of the mean, we need to pass the reducer. And in the lambda, we contribute to, so the lambda is a bit different because we have two local results to update. We have the local sum and the local mean, and so we contribute to both, as we did before in different parallel reduce.
Thomas?
Yes.
Does it work? Yeah. There is a question in the chat. What would happen if we put a reducer object that is different from the reducing law defined inside the lambda?
Wait, I'm trying to find. Oops. Where is the question?
The penultimate.
What will happen if we put a reducer object that is different from the reducing law? Yeah, same, undefined. I think we could have some kind of linter, static linter that would check if we have coherence between the two. But this is currently not diagnosed, and I think you will just discover at runtime that you have a weird result. Do you have more questions? Yep.
Question about the minlock type. We saw how to use the minlock in the reducer. What I wanted to ask is that, is there any, for example, here we can use like, I don't know, but I feel like we can use just an STD pair and use pair.first and pair.second. But I feel like it won't work if you have like a GPU, as we said before. Kokkos help us to make it work. If we change like the backend, just what I wanted to know is that is there any win apart from that?
Apart from us, can you repeat?
So I understand that here we use Kokkos colon minlock.
Yes.
Instead of, for example, STD pair to store two values, because because of the same case of the Kokkos colon max. So we wanted to work even if you have like a GPU backend.
Yes. So the minlock is the reducer.
Yeah.
The way the result is stored is a different type again.
Okay.
This is the minlock type.
Okay.
And it may be Kokkos pair, which is a portable stud pair. Not sure of the. No, it must not be because the name of the variables do not match. So I guess it is a different structure.
Okay.
Why? Not sure. Maybe to have a more meaningful, more semantic on the type, because you have val and lock, if I remember.
Yeah.
So instead of pair, which would have first and second, which is a bit less meaningful.
Yeah, less oppressive, yeah. So I have another question about the multiple reduction.
Yep.
Suppose I want to keep an array of reductors. So I have like, I want to keep an array with a lot of result of reduction. Can I put like a parallel for inside the lambda?
No, this is more complicated than that. If you want to nest parallel reduce, you need a special execution policy to do that. You cannot nest any of the range policy or ND range policy.
Okay.
You will need to go for team policies. This expresses the hierarchical parallelism. It depends also on the parallelism you want to express. You may not always need to parallelize over all dimensions. If your array of reduction is small, you could, if you have a small number of reducers, you may not need to parallelize over it if you have enough parallelism on the initial array.
Okay. Understood.
If you need to express more parallelism, then yeah, I'm not sure the best implementation.
Okay. Yeah. Thanks.
I love the slide. Where are the slides? Slides.
Tu alt-tab sur le... Alt-tab.
J'ai fermé le... Ah, non. Thank you. And actually, it's time for an exercise. In the grace cuts, so initially we didn't have any reduction, I think, but we find a source of reduction in the checksum. So the checksum will assemble all the values of your arrays, and we ask you to make it parallel. So it's a bit tricky because this is the function that will check that your implementation is correct. So yeah, you will have to check again on the sequential case whether you messed up or not your reduction. So one thing that I may not have mentioned is that I only showed examples with range policy, but the parallel reduce also works on MD range. And that's the range that's the execution policy you will need to parallelize the checksum. And yeah, you need to check that you still have the same result. So I propose you to start from where you left this morning. You may have done the implementation of the Kokkos parallel for. So this is where I left this morning. In the compute, I added the parallel for. I will remove now the for loop as it is now validated. And this is this function that you need, where you see that we have the same pattern as in the C reduction. You have two nested loops that read the values of an array called field and that contribute to a single value called checksum. So I'll let you a few minutes to start trying to apply the Kokkos parallel reduce. Don't hesitate if you have questions on this. I can do it with you as we are a bit short on time. So let's start. So we need to call the Kokkos parallel reduce. The first parameter is the string. So we name it check, let's say. We have, as we said, two nested loops, so we likely want an MD range policy. So there is no obligation of using an MD range. It could be a range policy with an extra inner loop. You are just, again, it's the same question, losing some source of parallelism, because you have an iteration space that is actually bigger than just one loop. So this is the object that we need to construct. Not sure of the best formatting. We have two parameters, if you remember. The first parameter of the MD range is the start indices. So as this morning, we start at 1 for both dimensions. And we need the this as a second parameter the end of the loops, the end of the iteration space. That should be it, a comma. And now we need to pass as a third argument the lambda, which will correspond for the two first parameters to the indices that identify the current iteration, so I and j. We have only one reduction to do, and this is a summation, so this is the simplest case. It's a summation over a type called real, so let's reuse it. We need this local checksum, and then we pass the body of the function. That should be it. Let me format a bit better. So this morning we didn't go that far in implement using view everywhere. For the CPU day, it shouldn't matter too much. And so there's the final argument, which is the global result that we need to pass to parallel reduce. It is a summation, so we can take advantage of the defaults of Kokkos, and that should be it. Let's try to compile. Is there a question? Is there a mistake?
Yeah, Thomas, you should use the local
yes.
checksum instead of checksum.
Well, let's try. We wanted to know. Let's compile. Where am I?
Good folder.
So in exercises, and we are in my Grayscott. So no need to reconfigure, it's already configured correctly.
You're not in the my.js folder, are you?
Yeah, well, I can go in it.
Bool serial.
So it didn't recompile the other file, which was called parameters, because we didn't change anything. It only needs to recompile the Grayscott file. And yeah, we have the error that we mentioned. It says in the lambda function, the assignment of a read-only variable checksum is not possible. We are trying to modify something that is read-only. So at least there is the language security on this. You can also put mutable here if you want to play. Let's not do that. So if you put mutable, it should allow you to do this modification. But again, it should not compile on GPU. And you shouldn't do that. Okay. Serial, Grayscott. And yeah, if you remember, this was the checksum. So, like this morning, we introduced the parallel reduce as we did for the parallel for, but we are still using a serial backend, so do not expect any speed up at this stage. Any question on this? If not, I have a few slides of parallel scan before letting Paul do the parallel backend. The final, which is Oh, yes, we have a question.
Yes, thank you. I would just like to understand why we don't have to make explicit, what are they called, views in this situation?
Why? Sorry, what?
Why aren't we using views?
Why we are not using views?
Yes.
Because we didn't have time this morning to do it, but I can do it online.
Here it works because we're on CPU. I'm recorded. It works because we're on CPU and we access the data. On GPU, that would be a different story.
Ah, okay. Thank you.
No, but you are right. Huh? We are supposed to do that.
But yeah.
So yeah, one function of the view, and for interoperability purpose, you can retrieve the pointer of the view. You know that the view only contains a pointer and a few metadata, other metadata. So for interoperability with C functions or for the rest of the world, it can be useful to retrieve the pointer and pass it. But it's for the interaction with the rest of the world. Here we are only doing Kokkos, so we should not use the pointer for just for this kind of purpose. Let's check. We didn't break anything. Oh, there is again. Didn't save.
That's what we are doing.
Okay, same result. Yeah, we also have other remaining. You can do it, huh? I'll let you do it for add drop. We would need to pass views and also use the Kokkos parallel for. And I think that's the only place. Yeah, here also, the initialization.
Oh, yeah.
It could be done, we have different ways actually to do this. The parallel scan. So we have seen parallel loops, parallel reductions, and there is a final, slightly different, again, algorithm that we cannot express easily with loops and reductions, is the scan algorithm. So this takes this kind of form. We are reading from A in this case, and it's called a cumulative reduction. So we will do kind of multiple reductions and store the intermediate results in a final array. So it takes this form. You store the initial value of A into results, and while you loop, you will take your previous result and add A, the value of A, into the current result. So you see that this is plenty of reductions. If you unroll this kind of loop, you will see that all elements of the array contain reductions. Here in this case, this is an inclusive, meaning that we start at A of 0, but there is also an exclusive version of it where there is a shift between result and A. You can find this kind of algorithm when you do cumulative integrals. When, for example, you want an approximation of a primitive, of a function, this will be this kind of algorithm you can use. And when you want to assemble sparse matrices in the format of CSR, the compressed sparse row format. In the Kokkos version, it's again a free function called parallel scan. Again, you pass a string and an execution policy, but in this case, we have a restriction. This algorithm is essentially one-dimensional. So it only makes sense in this case for one-dimensional execution policies. So it will not work in MD range policy. Yeah, something we didn't mention is that MD range policy is only for multidimensional more than 2 rank loops. We have again the integer identifying the current iteration. We have the intermediate result called here update. And as in this case of a scan loop, something we didn't mention is that in the previous algorithms, the lambda is called only once per value of the iteration value I. But in the case of the parallel scan, the lambda for the same value of I can be called multiple times. This is due to the nature of the parallelization of the scan algorithm. And so you have to take this into account when you will contribute to the result array. And Kokkos provides you this information. You should store this the update in result only when isFinal is true. That's all. This is the implementation of inclusive scan. If you want an exclusive scan, you need to put the if condition and do the storage before the update, the contribution to the local result. And this is a summation, a scan summation, but you can, as the parallel reduce, have different kind of scan. You can do a product, you can do different scan operations, and if you want to do that, it's slightly more complicated than the previous one. We don't provide built-in operators for that. You will need to create a functor instead of just a lambda that defines init and join, and of course the function call operator as we did here. And they basically have the same semantic as in the parallel reduce. They tell Kokkos how to initialize the private local results and how to combine them, because Kokkos does not see what you are doing in the lambda. So for the same reason. And that's all, I think, for the parallel scan. So if you have questions, or we can move on to the parallel CPU backend. So one question is, how are parallel for and parallel reduce different when we want to make the sum of an array? Maybe I didn't mention it. You cannot really implement the summation in an array with a parallel for. You will have data races, because all threads will try to, even if you find a solution to make the global variable available on the GPU, or you find a way to capture it in the lambda and try to update it from all the iterations, you will have data races. So the threads will not agree on the value they read and write. And that's why we provide a dedicated algorithm, the parallel reduce, that is meant to avoid this kind of data races in a performant way. Yes, the parallel scan was added a bit lately, so it's not available in the version 0.1 of the slides. I think we will provide an update in the evening for the slides we just presented today. And so, since it is a template function, I guess they use some optimized way to reduce instead of, yeah, just a comment, I guess. I think that's all. I leave you the place. So now we have seen, we have implemented the parallel, we have added the parallel algorithms in the Gray Scott equation. Let's try to make it run in parallel. And I will leave the place to Paul to present you how to recompile Kokkos.
Thank you, Thomas. Welcome back. So we are moving now to a new dimension. the parallel CPU, multi-threaded CPUs. So up to now, we use the sequential implementation, of course, sequential backend, serial backend, and we move to a different backend. So this is reinitialization in case you lost your access to the obtainer image, etc. It's just a recap. You can normally, well, you can have it in the chat because it was copy-pasted this morning. It's just the same. You don't need to duplicate the exercise folder because you did it already. Normally, that should be good for all of you, just to have the image just running again. So let's back to some theoretical aspect of Kokkos, the notion of backend in Kokkos. As I said this morning, you compile Kokkos for a specific backend. Here in the illustration, you have the serial backend on the left, or the CPU backend on the left, and the GPU backend on the right. We explored already the serial backend that didn't add that much, actually, compared to the sequential implementation, but just gave us the opportunity to use Kokkos views and parallel constructs. And now we are going to be more interested by those two backends, OpenMP and C++ threads. Most of the time, you just want to use OpenMP for multi-threaded CPUs. C++ threads is useful on Mac, given that, if I'm not wrong, the default compiler on Mac Xcode doesn't support OpenMP, so you use C++ thread instead. But beside of that, on clusters, on Linux, you just use OpenMP. And well, since we're going to use a backend that we haven't used before, then we have to recompile Kokkos, right, for this backend, to use this backend. So before that, how are we going to tell Kokkos to use a specific backend? So in the options of Kokkos, you have the Kokkos _enable and the name of the backend. That's the option that you use to enable a specific backend. Here you have the backend we have seen so far, the serial backend, and the two backends for multi-threaded CPU. So it's the name actually of the backend, serial, well, it's the default, but OpenMP, so Kokkos _enable _OpenMP = on, or threads. You can enable only one CPU backend, only one of the two at the same time. You cannot build OpenMP and threads backend at the same time. Serial is a bit special because since it's used for debugging, it's always on by default, and you can have one multi-threaded CPU backend plus the serial backend enabled at the same time. And you pass this option when you configure CMake, by instance, for OpenMP, -d Kokkos enable OpenMP = on. So just like we did this morning, where we compiled Kokkos for the serial backend, you will compile Kokkos again, but this time using the OpenMP backend. So you just have to use those commands. The difference between this morning is just now we keep the same sources because this is still Kokkos. We build in a different folder, right? We activate the OpenMP backend. Also, we want to use Arch native to use the microarchitecture of the CPU that we are using. We build it and we install it in a different folder. So this time, CMake install $home opt Kokkos OpenMP. Are there any questions just for this part? What about in the chats? Is everything clear? Will this part be the CPU CMD folder? That's something we'll see just a bit after in the afternoon. Is it possible to compile with a device backend and a host backend at the same time? Yes, absolutely. But we're going to investigate more on that next week. And if you're a bit lost in the work that we have done so far, you can restart from the exercise/CPU folder that contains the basic CPU implementation. Normally, you should be on par with this folder, minus some small details. Okay, do we have a working OpenMP backend compiled and installed? I can do it live as well. Okay, so CMake sources /src Kokkos like before. build directory build Kokkos OpenMP. CMake build type release. Kokkos enable OpenMP on, and also Kokkos Arch native equal on. I think I'm not missing anything with this one. Yeah, that should be good. Okay, so you see this here in the output of CMake that we have enabled the OpenMP backend for the host parallel part. Let's build and install. Okay, that's easy enough, and we install it. Okay, and now we have it. What we can do is, well, maybe if you want to do it, I think I will go ahead and do it just right now. We can recall the Hello World program, the test program, just recompile it with OpenMP backend and check when we call it that we are using the OpenMP backend. So to do so, I just go to the Hello World, exercise Hello World. Normally you don't do that, but it is just check to prove that, okay, we are using the good backend. Kokkos roots. Okay, this time CMake found that we use Kokkos and that it was compiled for the OpenMP backend. We just compile. Okay. And we pass Kokkos print configuration. That tells us that we are using the OpenMP backend. Okay, fair enough. Again, if you have a Kokkos program that you've compiled but you don't remember which backend you used, you can just call it with print configuration. It also gives us some information from OpenMP, like what is the thread pool topology. We are on a CPU of 40 cores, so two sockets, and each socket is 20 cores, and it gives you that we have a topology of 141. I think that's good. And now we have our OpenMP backend built and installed. Then we can use it on the program that we have worked this morning at the beginning of this afternoon and just compile it without changing anything. So I go back to the my.js, okay, and I do just the same. I have the command in my history. So let's see. We just made it Kokkos, and now just let's try to run it with the OpenMP backend. Is everything clear for everybody? Oh, I see there is a lot of... Oh, some people witnessed bugs in Kokkos. For Joseph McElroy, I'm not sure. Maybe you move the build directory somewhere. So maybe it's better, you're better off to remove the build directory and rebuild in it. Okay, we are done, and I just want to do something, yeah, let's just try to run it. OpenMP, Grace codes. Well, we don't see much a difference because the case is small, but there is something. Here, we have a message that is displayed. This is Kokkos initialize that tells us, hey, you are using OpenMP backend, but it's better if you set some OpenMP environment variables to obtain better results. So we just need to do export OMP procbind spread and OpenMP places threads. Okay. Well, it doesn't change anything on the execution speed, but now at the initialization, the variables exist. It's fine. Maybe we would like to go a bit more in the difficulty. Oh, well, yeah, by the way, you see that the checksum is the same. We've changed the backend. The program runs, it behaves as before. Maybe we would like, because a 10 by 10 program is not that challenging, I would say. If I'm not wrong, I will go with the serial implementation first, with the sequential implementation. I was told that the typical problem you want to solve is like 90, 80, 320 iterations, no output on the disk. So I run here the sequential. I want just to compare a bit the different implementations. And it runs in, well, I have in my prompt something that gives the amount of time we spent. We can be a bit more precise with time, but it takes about 6 seconds with the sequential implementation. Okay. If I do the same with our current implementation using the backend, the serial backend, what do we get? So this time we're getting something like 11 seconds, which is, well, not super great. We will give more details after, but a bit of a side effect of Kokkos is that since you make your kernel, but it's the compiler may have difficulty to understand that, okay, that's something that will be run for loop of large dimension, and maybe I can do auto-vectorization on that. So yeah, we lose some performance here. We're gonna gain them back in a bit later in the afternoon. And if I run with the OpenMP backend, it's not fair, but it's much faster because now we are using 40 threads to run it. There's more to say about this. Are there any other questions in the chat? Yes, Nihal Konchakti, but that's, so you have the Kokkos OpenMP, enable OpenMP, yes. It's not enabled by default, it's probably because you compiled Kokkos with that. Yeah. Oh, I see much difference. So Senwen Deng said that he doesn't witness any different. That's right. That's right. That's interesting. Are you sure that you are compiling with the different installed version of Kokkos, the sequential and the OpenMP one? Maybe try to double check on this. Yeah. So I have to move on. Oh yeah, talking about performance. No, okay. Are there any other questions about moving to the OpenMP backend? In the audience, everything was right for you in the room? And online? Ah. Okay, yeah. Michael is giving some advices. Okay, if it's so, we can, I can give the floor to my colleague to talk about more performance.
Yes. So we will continue on the topic of performance on CPU. So we just started to have runs using parallelism. And when we start doing that, we may want to measure how efficient we are when we are starting to parallelize. And we have different ways to do that. One way is doing scaling curves. So we have two kind of scaling we can measure. We have the strong and weak scaling. So the idea of the scaling is to get more information of how the application behaves when we add more resources. And so resources can be quite large. For today, we only care about adding more threads on more cores, but it can be nodes or GPUs. We have, as I said, two types of scaling we can do, a strong and weak scaling. The main difference is in the problem size. When we do strong scaling, we have a fixed problem and we add more resources and hope to get a speed up. We want a faster time to solution. And we can measure this kind of speed up. Whereas in the weak scaling, we keep the work per processor constant. So the global problem increases as we increase the resources. And the idea is to hope to maintain the same runtime, but to treat in the same time a larger problem with more resources, of course. So yes, as an example, if we have one processor and we have 1 million points, it doesn't change between the strong and the weak scaling. Whereas we multiply by 10 the number of processors. We take a situation where at one processor, we have 1 million points in both. And when we multiply by 10 the number of processors, in the case of the strong scaling, we keep the same problem, so 1 million. And when we go to weak scaling, we also multiply by 10. So we get 10 million points. So as I said, the strong scaling measures how the execution time decreases when we solve the same problem with more resources. So the ideal, if we note T of the runtime on one thread and TP, the runtime on P threads, the ideal speedup is that we divide by P the runtime on one thread. And this, we can measure then the ratio between the two times and do a curve of this value, the speedup, in function of the processors or the threads that we increase in the application. There are different also reasons that we do not measure the ideal speedup due to some overheads in the application. And you can have a look at the Amdahl's law that will put a limit on the ideal speedup that you can obtain based on the serial parts, and so the parts of your application that are not being parallelized, and that will put a limit on the speedup you can obtain. In the case of the weak scaling, as I said also, we measure how the runtime changes when we increase both the resources and the problem, but keeping the same problem, the same amount of work per unit of resource. So we hope the ideal weak scaling is that the time spent with P processors, P resources, is the same as the time spent with one resource. And here we don't expect a speed up, so we usually measure the efficiency. It's the same formula, but we have changed the definitions of the things we measure. And so we again measure this ratio and see how it behaves when we increase the resources. And again, we have a few limitations when the problem grows and when we increase the resources, we may have more communications, and that can limit also the ideal efficiency of one. So we are supposed to have an exercise on it. It takes a bit of time to do, so because we have to gather all the data for the different simulations. We have to do plenty of points for each thread. So I propose that we skip it. I have some results to show you. I did this exercise on the cluster we have in Paris at Idris, which is called the Ruche cluster, and that's where we actually, Paul and I, do the exercises today. So on the CPU partition, we have Intel CPUs. These are bi-sockets, so 2 sockets of 20 cores each, and a processor of at 2.1 gigahertz. So let's start with the weak scaling. So here, I remind you that this is the efficiency. So I'm plotting the time spent on one processor over P processors. And I change the number of processors. So remember that this also increases the total problem. The ideal efficiency is 1, and we see that, so I went up to 16 cores on the cluster, so I stayed using OpenMP also close, so I stayed on 1 socket. I ended up at an efficiency of 0.7. So yeah, we lose a bit of efficiency when we increase the number of resources. That may be due to we have a naive implementation. There are other parameters that we didn't really also mention in the MD range policy that could improve this efficiency, which this parameter is called the tiling in Kokkos, that could improve the cache usage during the execution, and maybe, I didn't do the exercise, benefits and improve this efficiency. But to improve it, you need to do a better analysis, as we saw using tools that we saw, for example, yesterday. I also did a strong scaling. So on the same node, this time I went up to 32 cores. So we see that we have kind of 2 regimes between 1 and 16. So parallelism is not ideal, so we lose a bit of performance. But we have a break at 16, and when we go to 32. This is likely due, I didn't check, but likely due to NUMA effects, as we saw yesterday. We have a NUMA region at 20 cores. And when we go up to 21 and above, we are starting to use 2 NUMA regions. So there is the same question as we saw yesterday about first touch, because this is OpenMP. This is the same notions as we saw yesterday. If you have questions on the way we do allocations on Kokkos also, we can answer on this. But in this implementation, it was quite naive, so we didn't pay attention of the first touch. So this is likely due to this, that we have this loss of performance when we reach the second NUMA region. Is this clear for you? So you can do this kind of plot also on the resources you have on MUST or on your cluster on satellite sites, and see how it behaves. if we are good with that, unless we have also questions on Discord. So yeah, you answered. Yeah. Okay. The final part of today will be about vectorization. Another way to improve our application after parallelization. So what is vectorization? So I think you already have had some lectures about this. I will maybe repeat a bit. So the idea of vectorization. So we start with a problem where we want to add two arrays, a vector called A and a vector called B, and a naive implementation, a scalar implementation, is to treat all elements one by one. This is what we call a scalar implementation. So we will do an addition between the first element of A and B and store the result, and then go to the second element, etc. But some modern CPUs have instructions that are able to do multiple computations at a time. For example, 4 distinct additions in a single, in the same number of cycles as you would do with one instruction. So this is what we call SIMD. That stands for single instruction, multiple data. So the same instruction applied on different data. And so if you can, if you have a CPU that is able to handle n times data in a single instruction, you can expect a speed up of n. So this is ideal. We likely want that, and we will see how it goes. How do we do that? There are multiple ways to vectorize. You saw that yesterday in Fortran, you could add some flags on the command line and hope that you would get a vectorization, and I think you got it. In C++, it's a bit more difficult. One way to achieve vectorization is also to use special functions that we call intrinsics, and that are provided by the compiler and dedicated to the CPU you are using. And so when you start using intrinsics, you are starting to lose portability. So you have a different set of instructions. Well known for x86, for example, are SSE, AVX, AVX 512. On ARM, you have other sets of instructions like Neon, SVE, SVE2, RISC-V, others. And if you invent a new CPU, you can also invent new intrinsics related to your CPU. So you start to see that it will be difficult to have a portable source code because you start to have instructions that are specific to your CPU. So let's take an example. If we want to add 2 SIMD vectors of double using intrinsics. So on using AVX2, you will need to include a special header file, which has this name. You need to use this kind of data type. You see that it starts with 2 underscores, so it looks a bit dangerous to use. So you declare 2 variables A and B. And if you want to perform an addition between these two, you cannot just call A plus B. You need to call a special function that has this kind of name, add packed double on A and B, and store it in A. So once you have done this exercise, you are happy because you vectorized, but this vectorization is only available for some Intel and AMD CPUs. And if you go to ARM CPUs, it doesn't even compile. If you want to do this kind of exercise again for ARM, you will need another special header, another special type. This is the same logic, actually slightly a bit different in the case of SVE. But yeah, you need to call special instructions, special types, so you have divergent code for different CPUs. So this is time-consuming to implement, repetitive, and a source of error. So this is a way to vectorize using intrinsics. So if you do that, at least you are sure that you will vectorize. It's a bit painful to do, but you are sure to get it. There is another way, which is the auto-vectorization, and that's what was done yesterday in Fortran. You let the compiler find sources of vectorization. And usually it has some usually good heuristics for one-dimensional cases where you do quite simple operations. You may also need to help it a bit using pragma notations, where you will declare, and that's where it is more difficult in C++ than Fortran. You will need to declare that you do not have dependencies between read and write operations. As the compiler has to do some transformation in your source code, it must be conservative. It shouldn't change the result. It must be sure before doing the transformation, and sometimes it cannot prove the transformation, so it doesn't do it, even though you know that it should be possible. And you can help it using some annotations. So this is slightly more fragile. You are never sure that you will get the vectorization with this kind of approach. But at least when you get it, you didn't transform yourself the source code. And on that, Kokkos helps a bit. It can add some annotations internally on the loops it will implement. But same problem of aliasing. It's still difficult because it is still the responsibility of the compiler. In Kokkos, we don't have we cannot force the compiler to do that. So another strategy is to use vectorization libraries. There are many on the market as Kokkos. And the idea of this vectorization library is to provide a higher level abstraction to manipulate the vectors that we manipulated in the AVX2 and SVE implementations. It's also a C++ API, so as we can take advantage of overloading operators like plus, all the regular math operators. And we can play with templates and ifdef to hide all these non-portable intrinsics to have a portable abstraction. So the idea is, instead of having this kind of code which is not portable and only works for AVX2, in Kokkos, but you will see another library with Eve next week that also provides some SIMD functions. In Kokkos, you need to add this header file, Kokkos SIMD. It doesn't depend on the architecture, so it's always the same. And there is this unique class, SIMD. You need to provide the type of data that you want to store in your SIMD vector. And you recover the more readable operators unless of a free function. And so this adapts to any CPU. You will just need to recompile to get the correct intrinsics and the underlying intrinsics. A note on the C++ standard. This is proposed to the C++26. I don't know if it's yet finally accepted or not, but there will be likely a similar approach in the standard where you will have stud SIMD, again of the type you want, and with all the basic operators, math functions also, to help you vectorize your algorithms. The Kokkos SIMD tries to follow the same API, so it's a work in progress. It's because it has also changed more recently, I think, in the proposal for the standardization. So I don't think we have the final naming. And yeah, it solves the portability between the CPUs. But more than that, Kokkos, as we will see next week, also works on GPU. Also provides kind of a fallback of this SIMD, which is essentially a CPU issue. If we start to use Kokkos SIMD also on GPU, it will fall back to a scalar implementation and still works, which is quite good because then we can still have the same source code which works on CPU and GPU. So let's dive more in details in the Kokkos SIMD implementation. So we have this, as I said, type SIMD. It's in another namespace because it's a work in progress. It's in the namespace experimental, so don't be afraid. But it makes some slides a bit verbose, but it works. Don't worry. We have also SIMD mask that will allow you to do masked operations. So operations that do not apply on all vector lanes of your SIMD vector. And we provide all the basic operations that you could expect, all arithmetic, bitwise, shift, and comparison operations. So that allows you to do this kind of code, which if you would write it using intrinsics would be quite a few lines and not clear at all. There are auxiliary functions that allows you to load data into this kind of SIMD structure from a pointer, from ranges, etc. The same for store. And the math functions, so you can call a Kokkos cos, a cosine function on the SIMD type. As we just did, if you want to get the correct intrinsics on your when you compile Kokkos, either you know your architecture and you provide by hand the correct architecture using the CMake options, or you let Kokkos discover it if you plan to run on the same platform. And that's the Kokkos Arch Native that you used earlier. We saw that you need to pass a template parameter in SIMD. And this type can be, it is limited. You cannot provide anything you want because it's related to the underlying platform. So this mainly concerns float double and some integer types. You will not be able to pass any vector types or any custom type. Some platforms may have different sets of instruction sets. And so this raises the question of what size of SIMD it will use. And by default, Kokkos uses the largest vector type. So, for example, in AVX2, you can do 4 operations on doubles, and you can go to 8 on AVX512. So Kokkos will, if it is available in your platform, Kokkos will use the version with 8 doubles. It's not always the optimal, but this is the default. And you can specify it if you know the value you want. But be careful because you are starting to lose a bit of portability. If you choose one value on one platform, this may not exist on another platform. So you need to implement your own logic if you want to be portable. And SIMD is actually an alias to this basic SIMD class, which has a second template parameter if you want to have more control of the ABI, the instruction set you want to use. So yes, some examples of supported instruction sets. So just to say that they are not always available. So on AVX2, you can use all data types, but with the value 4 for the previous n value that we saw in the previous slide. But if you go to 8, then you cannot do 8 operation on double. It does not appear in this list because it's not available in this instruction set. So that's why I was saying that it's, if you start playing with this kind of parameter, it's not always portable. Yes, we have a question.
Yes, it was about the previous slide. Yes, if we don't know the amount of, the maximum amount of elements in a vector in our system, so is it just going to pad the last one? If it doesn't, if it's not if it's like 8, if it's 16 and it's not divisible by 16, the amount of elements?
Kokkos will choose the largest one, so it will always...
It will always do padding or something?
What do you mean by padding?
Like the last part of the loop that doesn't fit.
There is no padding in this in the SIMD structure? Or you mean when you do an allocation on a stud vector or...
I guess I'm not really
sure. If you
do
dynamic allocation, it's not related. So if you want to have a multiple of your SIMD size, it's your responsibility.
Okay.
How to manipulate this new type in Kokkos. So you have a default constructor. So the values will be uninitialized. So be careful of this. You can pass one value, and this value will be broadcasted to all elements of the underlying SIMD lanes. You can initialize also all SIMD lanes providing a lambda. So this lambda will be called on every lane, and the return value of the lambda will be stored in the corresponding lane. And what will be useful for the Gray-Scott equation is to load the values from memory. So you have an existing array in memory that you dynamically allocated, and you want to manipulate parts of this allocation using SIMD. So you can pass the pointer, and it will construct an SIMD type based on this pointer. It will load the data and store them in the SIMD type. So for example, if SIMD is of size 4 doubles, it will load 4 contiguous doubles from the array, from the starting point of the pointer. So we want to show you an example of how we will transform the loop when we start to vectorize an algorithm. So we start with the scalar loop that we saw earlier. We have a parallel for, we want to loop over n iterations, and we have the lambda, and we do some work based on this integer. How this will be impacted when we start to use SIMD type. As we vectorize, we will treat multiple elements in a single iteration. So we need to decrease the size of the iteration space. We need to divide it by the vector width. So we will do less iterations because each iteration will do more work. This is an important note if you want to understand how to vectorize. So instead of iterating from 0 to n, we will iterate from 0 to n over vector weights. So we mentioned on the first slide that we wanted to do an addition on two arrays, A and B. So let's try to do this. So we declare two views, two one-dimensional views, A and B of size n. So a scalar implementation of this addition. So we add B into A. So we just call the plus equal operator on every element of each array. Now let's look at the addition in a vectorized manner. Slightly a bit scary maybe, and we try to not be too scary. So let's have a look at each line. So I said that these symbols are in the Kokkos experimental namespace, so we just create an alias so that it fits on one line. We get also an alias called SIMD type, which represents an SIMD double. I mentioned that if we want to vectorize, we have to decrease the iteration space by the amount of the size of the vector type. So instead of looping over n, we loop over n by over size of the width of the vector size. So we get an integer, but this integer represents the starting point from multiple elements. So it represents the starting point from I times SIMD types size. This index represents the same index as we would have here. We mentioned that we can load data from an array, from a pointer, and store it in SIMD type. So we use, we dereference the array using index, and we take the address. And this constructor of the SIMD type is responsible to copy the data from the array into a local value, local type, local object called A. We have to pass this flag default. The flag default should be defaulted in a later commit. In a later release, you should not need to specify it by hand. For now, it's mandatory, but in a future change, it should not be necessary anymore. So we have created A and B, which represents two local copies of some values of the arrays A and B. We perform the computation on these SIMD types. So here we are ensured that we have a vectorized addition on the local values A and B. And then we copy back the content of A into the global array A. And in this way, we have a vectorized implementation of the addition. So it's slightly more verbose. If you want to go in this direction, it means that you really care about the performance of this algorithm. That's not the natural way to start with when you start parallelizing in Kokkos. You usually stick to a scalar implementation. And if some algorithm is a bottleneck, you can consider this kind of implementation and vectorization. Also, if the compiler could not auto-vectorize by himself. If you get the auto-vectorization, you don't need to do that. So not sure we will have time to do the Grayscott case in this SIMD way. I will just show you the source code of the solution. The idea, if we want to vectorize the Grayscott equation, it's even more complicated than the addition of two vectors. The idea is that you have a 2D iteration space. You have to be careful over which dimension you are creating your SIMD types. So that's what I mean by identifying the contiguous dimension in your Kokkos views. You have to adapt the iteration space as we did when we vectorized the addition of A and B. And then you have to replace a lot of the real scalar types, objects that we have in the Grayscott by SIMD types. So that's the purpose of the exercise. I will show you directly the solution of this exercise. How much time left? It's already... Okay. Okay. So
Just there is a question in the chat. How does it handle the peeling part?
The what? Sorry?
The peeling. I'm not sure to understand what it means. Luke, are you talking about the tailing? In case the number of elements is not a multiple of the SMD
so, yeah.
width?
So I will answer the question maybe after. So we have to include this new header, Kokkos SIMD. We also did an alias of the namespace to have shorter lines. We have added also some SIMD types, some shortcuts, SIMD of real and another SIMD types, which will be scalar. And that will be related to the question, I think. So,
they mentioned the peeling of the first non-aligned elements.
To my knowledge, it's not handled. You have to do it. The vectorization is much more manual. So you have to separate non-aligned accesses from aligned accesses. So you will have, I think it could be similar to to the strategy we did to handle the reminder, because your iteration space may not be a multiple of the SIMD width. And so you have to take care of this. One way we did that is to template by the SIMD type, so that we have two calls of this function, one with the largest SIMD type, so that we have the maximum performance, and we will have a few more elements that need to be treated, and they will be treated with an SIMD type of one element. So how does it changes the source code? It changes a few things. So as in the vector addition, we need to adapt the iteration space. So it changes only in one dimension, because this is the dimension which is contiguous. So the first dimension is not changed, but the second will have less elements, because we will treat more elements in one iteration. So again, we have this offset to do, as we did in the vector addition. And instead of here, we used to have real or reading from the arrays U and V, UTemp and VTemp. Here, instead, we pass pointers and offsets that are represented by J0 and I. So we do a lot of loading, so we are creating a lot of temporaries. And if we go to the usage of these temporaries, you get back here, if you recognize, the stencil of the Gray-Scott equation. So here, this is quite similar to what we used to have in the scalar implementation. But instead of using only doubles or just a real type which mapped to a double, we are now treating multiple elements at once in a vectorized manner. So in this case, you expect, if you have a VX2, for example, a speedup of 4 because you treat in the same number of cycles 4 elements. So I showed you how to load memory, and this is how you store your results. So your result is in a SIMD type, and you can store it in the global array using the pointer. This is here a good usage of the data function that you have access in the view, and you pass the SIMD type, and this will store this result in the global array. And in this way, you have a vectorization implementation of the Gray-Scott equation. Okay, let's try to build it. Where am I? So we can reuse the OpenMP build of Kokkos. Kokkos root is okay. We can try. Do you have questions in the meantime?
So I know that this is a rather difficult exercise. Yeah. That's why we put it in the end. This is, well, for sure it's more complicated, but it's worth it because the gain in performance is meaningful on CPU.
This is the command you use to run?
Yes, you have to have Gray-Scott _ CPU SIMD. This is a bit too fast. Is it?
And what did we get from the scalar implementation?
Oh, because run it sequentially first, maybe with only one CPU thread.
Build. Yeah, we are using.
Yeah. This is one. Also, this is sequential implementation, 6 seconds something.
So you can control the number of Kokkos threads you want to use.
Okay.
So, oops. So we went from. Sorry, I lost the result. Six seconds to 2 seconds.
And the implementation in Kokkos using the SYCL backend was 11 seconds. So we moved from 11 seconds to 2 seconds.
And in this case, we have a VX512, so we are supposed to, at maximum, get a speed up of 8. And we get a speed up of 5, a bit more.
5, 6.
Yeah. So, it's worth the pain.
It's worth the pain.
Do you have any question on this? Let me have a look at the chat. Yeah, all of it have been answered. So I will.
We should pass on.
Yeah, we'll pass on the bonus. It's more SIMD. Yeah, just one slide of conclusion before leaving you for the break. So we saw that Kokkos provides this morning some useful data containers called views. We saw how to use parallel for and parallel reduce to parallelize basic algorithms. We saw that we can use range policy and derange policy for basic usage. And if you really want to push performance, you can go to SIMD implementation, but with more pain. But in some situations, it can be worth it. So thank you for attending this Kokkos on CPU. Next week, we will be talking about GPU and the few modifications you need to make it GPU ready. Not a lot, actually. And that's all. Thank you for attending. And yeah, we will make the slides available in the evening. And they tell me that we have 20 minutes of break. And we get back at 4:10. Thank you.
Okay, we are back on Glasgow School. So for the last part of today, so we'll do some precision stuff with Vincent. But before, little Larsen, before this this part with the precision, since we get some question during the break this morning, we'll talk about Fortran, the oldness of Fortran, and why some people are doing really, really big function for no reason apparently, but you will see that there is a reason. And after that, the precision part. So Vincent, it's up to you.
Thank you. So once more, Vincent Lafèche from UJC Lab. And to answer the question about why keep with Fortran when it has so bad reputation, we want to show some example of what modern Fortran brought from the start, from 95. So a lot of Fortran is linear algebra. BLAS was initially written in Fortran. LAPP was initially written in Fortran. A set of two libraries, LinPack, linear package, and eigenpack, eigenvalue package, and they merge. And now they are the standard tool to measure the power of computers, supercomputers. So as you can see here, in old-style Fortran, what you would do to have double precision, the general matrix multiplication, DGIM, a famous BLAS routine, would require 13 arguments. Of course, you have A, B, and C, the two matrices CC of the product and the matrix of the result of the product. But you had also to specify the number of line, column, and the column of the second matrix that were involved in the product. And not only the number of lines that you would use, but usually in Fortran, as you would add static matrices, you would expand, you would define a much larger size in memory to handle potentially larger matrices. And so you needed to pass to the matrix product the size in memory of the two long lines that were not occupied in order that it would know where to go back for the real second line. It was not stored after 3, in this case, line, but maybe 30, 300, 3000. Okay. So in modern Fortran, you just call GMM with this BLAS 95 module because it's an interface that encompasses, okay, so here is the generic call to generic matrix multiplication in Fortran 77, but you don't specify the type anymore, not the S for single, D for double, C for complex single, and Z for complex double, and then you mix two of them. You will call them with the same name because they have the same list of arguments with different types that are defined over there and repeatedly. What is more, in Fortran 95, you can define what is called optional parameter. And as they are optional, if your matrix is not transposed, you don't pass the normal transpose. By default, it is not transposed. If you want to specify it, you can pass it. So with BLAS, you had already a large reduction of parameter, 13 to 3. It is also true for LAPP. And the biggest in LAPP has 29 arguments, so it's a mess. You don't want to be programming like that. And the equivalent with the modern Fortran, okay, so it's below, but you have only 20 arguments because a lot of them were optional. Okay, so this was the part for Fortran. Any question on the question? No. So I will move on to the real part of today that require some calling to the muse. Oh, mathématiques sévères, je ne vous ai pas oublié depuis que vos savantes leçons, plus douces que le miel, filtrèrent dans mon cœur comme une onde rafraîchissante. Sorry for the French. So we'll be dealing with accuracy and precision. Floating world. So in Japanese, it's an expression to speak about woodblock stamps, woodblock printing. But this is the stop of poetry for now, and we enter bloody things. We are used to numbers. We know them from elementary school, and we have learned on top of them. We know a lot of kind of number, real number, algebraic number, constructible number, decimal number, we like them, we are paid with decimal number, we are evaluated with decimal number. Everything is decimal in our view, in our day-to-day view. As computer scientists and information technologists, we also know binary number. Most of the time we use binary integer, but we'll see a lot about binary floats. And particularly, we'll start with what is floating point. Most of the time, they are considered primitive type of our language. Float, double, long double, quad, half. The name change a bit depending on your language. They are not primitive. We'll see that they are some kind of object. We'll see a lot of cases where computation don't turn out as expected. So why? How does it fail? What are rounding error, conversion error, propagating error, and how it composes? And we'll see that sometimes getting some heuristic view of what you are computing is more important than the computation itself. If you don't know the general behavior of your computation, it's hard to pick what could go wrong. And sometimes a rough estimate, what you would do with asymptotics, for instance, is the way to save on epsilons, to save on accuracy. This time, this year, it's longer than usual, so I can delve into details, and we will speak about non-dimensionalization, and so-called formula entropy reduction, how it can be reconciled with performance, on how to reconcile abstraction and accuracy. Some hints also about why the geometrical computation are so hard. Let us start with bad news. Up to now, we can produce bugs without anybody getting too fussy about it and asking us to produce methods and deontology. But these numbers, this floating point number, can cost a lot of money and kill some people. So in '82, so it's not young, in Vancouver Stock Exchange, they had coded things without much reflection, and they were truncating instead of rounding. On 4 digits instead of 3, the error accumulated over 2 years, and the value of the whole share stock market index presented a 50% error after 2 years. So quite a lot of money. The most famous one is the one of Patriot missile during the first Gulf War. The time counter was a floating point number. Don't do this. So absolutely don't do this. For interception, so the rounding error accumulated over some days, and it introduces with some milliseconds of error, a 600-meter error, 28 people killed, 100 injured. This offshore platform next to Norway in 91, it was more complicated case. The program of finite element was not accurate, plus rounding error. The stresses were underestimated by 47%, $700 million in one go. It's a bit different this time. It's an engineering error that led to floating point error, but when Intel in 94 realized that the division was wrong one time in 1000, they had to recall a lot of processors for $500 million of the time. And the one that were really outperforming with losing $10 million a minute was the Knight Capital Group hedge fund. So once more, it was not only floating point error, it was floating point combined with bad deployment. They forgot to deploy a distributed system on one of their servers that kept getting some old code that had not been erased working. And as it was producing different results, it made a lot of transaction fail. In 45 minutes needed to stop it, they had lost also almost $1 billion. Okay, so these problems are well known. From 91, you have this paper from Goldberg. Please read it. If it's too long, I can point you to some paper on archive, which is revisiting the too long paper. You know the author. The statement here is floating point arithmetic is considered an esoteric subject by many people. So how much esoteric is it? When we speak of floating point number, we think about the format IEEE 754. And a floating point number is a kind of scientific notation, significant times base at the power of exponent, with significant an integer number, and exponent an integer number. Okay. This general scientific notation would not be uniquely defining each number, so we take the standard form where the mantissa is a normalized significant, and we keep the mantissa between 1 and the value of the base. In base 2, it's always 1, the most significant digit. But we'll see it's not always the case, one thing at a time. So we have, for the float, the most common one, 32 bits, including one sign, 8 bits of exponent, and beside this, 23 bits of mantissa. 23 bits plus the most significant bit always set to 1. So we have 24 bits of mantissa, in fact, 23 of them being stored, and the most significant being supposed to be always 1. The double precision, 1 bit of sign, 11 bits of exponent, so from minus 1024 to plus 124. 52 bits of Mantissa, 52 stored bits, which means 53 bits in total with the most significant bit. And then the third one, the long double, is almost used by anybody. Nobody uses it. Okay. We pay for it. For 45 years, we have been paying for this. Nobody uses it. It's a pity. You get 3 more decimal digits of accuracy computing with this. As it was not so much used, it has never been vectorized. And it would be a bit odd in memory. So William Kahn, that we'll speak of, asked the Intel engineer in the early 80s, over how many bits can I propagate a carry in one cycle? 67, okay, so it will be 64 plus 3 extra digits for computation, 3 extra bits. We will see about it. On the last one, we'll have 2 rough hours with me because I will say bad things about half precision. Okay, so these are the formats about the storage in memory. But when you compute, the FPU registers have 3 more bits as the least significant one, a bit like when in elementary school you were computing with more decimal in order to round properly. This is exactly the case. We have the guard bit, the round bit, and the sticky bit. We'll see more about them. So hopefully, we have only these 4, let's say 5 when you include the quadruple precision that is emulated. I have not seen it in silico. But you can check this URL where they present all known formats, older formats of floating point before the IEEE 754 would standardize everything. They have 3 pages like this. So we are lucky. And we are lucky thanks to this guy, Professor William Kahn, the father of floating point. He got the Turing Award in 1989 for his fundamental contribution to numerical analysis. He started in 1977 as consultant for Intel FPU, the x87. And they announced a proposed standard for floating point. And it was ratified in 85. So, okay, 40 years that we all are ruled by this kind of floating point. Please visit his page over there. It's a treasure of information. Okay, so the standard has been evolving. It's an ISO standard, IEC by the last version. It has been evolving regularly, and we expect still more things. Because the standard is not only about format. All there has to be said about this has already been said. There are also statements about the accuracy of the operation. There are also API that are guaranteed to be provided for your number. And when you look, we'll see some of the representation of float. If you want to encode the float for 1, the sign is positive, 0. The exponent is 127 because by definition here we take 2 to the power e minus 127. So when you encode 127, it means 2 to the power 0, which is 1. And all these 0 are after the most significant bit at 1. So it's 1 times 1, plus 1 times 1. When you want to move to 2, you increase the exponent, 128 minus 127, and you don't change the mantissa. When you want to add 1, okay, we are 2 times 1.5. So 1.5 makes the most significant bit after the next two most significant bit of the mantissa to 1, and so on. Okay, I will not go through all of them. You can use the link below to represent your favorite number or to play with this format. So you have here some example of number that can be represented exactly up to here. And then starting at 1/5, it's not quite true because 0.2 has no exact representation in binary. It's a decimal number that has no exact binary representation. So of course, 1/3, the square root of 2 pi, neither of them have an accurate, an exact representation. It means that when you compute them, the FPU is setting a flag inexact. I had to round this number, so the result is inexact. So in any realistic computation, don't try to trap this flag. Your program stops immediately. Most of the computation will set the inexact flag. Okay, so 0 has a conventional representation because you could not express it in the way that is here. It cannot be expressed as a product of 1 plus something times 2 to some power. So when you have all zeros, it's 0. And when you change the sign, it's a different 0. It's 0 minus. We don't see much interest immediately, but it's helpful when you will be doing complex number computation, depending on the sign of the 0 on the imaginary axis, you will have very different results. Okay, so if we put everything to 1, almost everything, except the sign bit, we go to 254 for the exponent, minus 127, and we put all the bits to 1. This is the largest float. It's 10 to the 38. And when you increase by only 1 bit, so you have this number, and this is the conventional representation for plus infinity. So we say that every number that starts with this 255 exponent will be some special representation, including the one for not a number. So plus infinity is a good way to express overflow. And minus infinity is also some kind of overflow. You just change the sign over here. But when you have 0/0 or some invalid operation, you want to store the result as not a number. And as I told you yesterday, there are two kinds of not a number, the quiet one that will propagate in your computation, and the signaling one that will abort brutally your computation. So choose the one you prefer. Some more interesting things about QNAN and the SNAN, they are not in only one exemplary. You have a ton of possible quiet NAND. You only need the next to most significant bit to be 1, and all the others can encode what kind of specific NAND you want. You can pass a message through your NAND. Up to now, it was black magic, but the next standard will provide an API to set this payload. The same goes for signaling NAND. You may want to know, okay, my program brutally stopped, why? When you go on the other side, the smallest positive float with an exponent of 1, which is minus 126, is the so-called smallest positive float. But we can go below. If we subtract 1, we have the largest denormal positive float. Denormal, what does it mean? It means that for this category of number, when the exponent is 0, the computation will suppose that the bit that was usually 1, the most significant bit that is not encoded, can go to 0. We'll speak more about this denormal number because the reflex is 10 to the minus 38. And when you look at double precision, it means 10 to the minus 308. Nobody needs this number in computation. They will never appear. They will appear. Okay, so can we look at this exact representation? Okay, in C, you have this percentage %A format that will display 1 at 1, 2 times 2 to the power of 0. 2 as 1 times 2 to the power of 1. 3 as hexadecimal 1.8, which in binary, which in decimal would be 1.5, because 8 over 16 is half, 1/2. And so this representation is exact. It does not depend on rounding the last decimal number. How many decimal numbers should I keep? When you store floating point number, please do it with exact binary representation. C++ use xfloat and default float to come back as I/O manipulator. Fortran is very crude in this respect. You can dump the hexadecimal of your float. Python can do it with the .x method. And for Python, float means double, but not a problem. Ada has what one calls attribute to get the exponent and display the image of the exponent of a float, as well as display the image of the fraction of a float. It's not very different. We can do it in Rust, but it is not yet, as far as I know, in the standard library, so I had to define a component extraction function. And the display is the same. At the time before IEEE, when you wanted, yes, it's too small, but I cannot expand it, this one. The slide will be soon on view. There was some Makar routine that you would call to give you P, the number of digits of the format you are referring to. D is the digit, beta is the base, because some people were storing binary floating point, some people were storing hexadecimal floating point, some people were storing decimal floating point. We'll talk a small bit about it. So nowadays we have the half precision, single, double, extended, quadruple. I played with the octuple precision. It is very slow because it's emulated. It's floating point on 256 bits. The largest one is CFS, astronomical library, very old, I would say 40 years old. They have a special format with 384 bits. And when you call Makar on this format, you get the proper information. You can also use it on recently, some years, maybe in C23 norms, you have decimal 32, decimal 64, and decimal 128 floating point number in base 10. We'll see why. Okay. So instead of this routine written initially in old Fortran, Macar, it is part of the BLAS and LAPP library. We want some standard API. Each language has provided you some way to get to what Macar would provide you in the old time. You have the numerics limit in C, C++, and Python. In Fortran 90, you have the radix, digit, range, epsilon, and precision that give you all this. And so you can access for a given number what is the exponent of this number, and what is the fraction, meaning the mantissa of this number. So Fortran 90 was still concerned with the older format. So it was not yet IEEE standard notation that arrived in Fortran 03 on the ADA language, as well as some standardized way to access this detail of the model. Okay, so let's start with easy computation. 1 plus 2 equals 3. If your computer doesn't do it, we'll have problem. But when we ask something that seems as simple, 0.1 plus 0.2, it's not quite 0.3. Really? Okay, so you take a variable in FP32 for single precision, FP64 for double, FP80 for long double, FP16 for half precision. And you have 3 variables, you initialize it like this. And when you display more digits, this is what you find. There is a small bit at the end for A, except in half precision where there is a small bit below 1. The same for B, almost the same for C. And when you compute the sum, it has the same problem. But the sum of the false representation of the number is the false representation of the sum. So not so bad. Surprising, but not so bad. In double, it is worse because the sum of the wrong representation is not the wrong representation of the sum. And we'll have problem when we suppose that they should be equal. Okay, we have the same problem with half precision. They have a bad start. Okay, so you can play on this site in many languages. They have the same problem. So it's a problem that you need all of us computing people. It comes from the fact that the decimal number are not a subset of binary number. This is quite the opposite. Binary conversion, converting your decimal number to binary, needs some rounding. And this is why your 0.2 in base 10 has this kind of infinite representation in base 2, on the representation being infinite. When you convert it to a finite float, it's in fact this exact number. So when there is a circle around the mathematical operator, it means the comparison is done with rounding. And so we think about 0.2, but the computer says, okay, it's 0.2 plus 2.98 part in a billion. Okay. We should have stuck with the integers. Kronecker was right. Okay, so let's look at the math of this. Decimal, we know them, we like them. It's an integer over 10 to the power of an integer. It's the ring of the integer extended by 1/10. And the binary has the same structure. It's the ring of the integer extended by 1/2. So every binary number that we'll store in our computer will have some exact decimal representation. Yes. But as we have seen, not all decimal numbers are binary. 1/5 is a decimal, but it's not a binary. It has a very practical application. Don't use floating point number for any kind of financial application. Okay, maybe for your home budget or for the budget of your small community, it can be enough. Well, but when you get serious, you will lose sense at some point. The banks don't like it. Okay, so each of the operation, arithmetic operation, plus on multiplied, there is closure. All binary number have a sum that is a binary number, and the product that is a binary number. The sum and the product are commutative. The sum and the product are associative in binary. They are distributive one over the other. There is a total order. You have the transitivity of the comparison, the antisymmetry, the reflexivity, and so on, as well as the totality. Every pair of binary number can be compared as lesser or equal or in the opposite sense. There is no third choice. So binary numbers are good to go. And topologically speaking, the set of binary number, even if it's a small subpart of the decimal number, which is a small subpart of the rational number, they are dense in the real. So in principle, we should be able to arbitrarily close approximation of any real number. But we don't have binary number. We have floating point number, and this is the finite part of binary number. So we lose the closure. The sum of two floating point number has not an exact floating point representation in the standard we have. We can always find some example where it will not fit. The same goes for the product. And it means that we will be rounding the result to the closest floating point number we have. On top of this, we'll need to take into account overflow, underflow, inexact operation, and we'll represent them with plus or minus infinity for overflow, with 0 for underflow. 0 doesn't always mean 0 in floating point. The 0 of floating point is a number smaller than 10 to the minus 38. 10 to the minus 45 because we have the denormal number. And even when we have not this catastrophic underflow or overflow, most of the time, we compute inexact result. We keep the commutativity. Hooray! We lose the associativity, and it's a problem for our activity in HPC. We lose the distributivity, and we almost keep the total order, except with not a number. Not a number, you can say that it is a number which is at the same time lesser and bigger than any other number. So if you have a not a number in a sorting routine, it's a problem. And topologically, the floating point number is a finite set. 2 to the power 32 elements, it will never be dense anywhere in R. So, some basic point about rounding. You have some curly X here, which is a floating real number on the line of real numbers. It always falls, okay, when it's not too big, between two representable floating point number. Let's call them hard X minus and hard X plus. There is some not floating point number, but real number, which is the average of this interval. And so your number, curly X, will fall most of the time in one of the two compartments between m and x plus or m and x minus. Which means that when we will be rounding x to the closest in this case will be x plus, and the error of rounding will be half 1 ULP. ULP is 1 unit in the last place, which is the quantum of accuracy your specific format is providing you. Okay. But if I want to be able to select if my computing number is closest to this one or this one, it means that I have extra bits to do the computation. If I have only one bit, I will fall in between on this average, so I will not be able to select it. If I have a second bit, I can know that I am above M or below M. And let's take a third one to be sure. And if with this 3-bit I still fall on the middle M, then I have to make a choice. So in primary school, the choice was rounding above to have a bigger grade. But the finance people do not like this. They prefer that half of the time you round above, half of the time you round below. So to keep some deterministic aspect to this rounding, the financer rounding, the banker rounding, so-called, is if you would have an even representation, if you have to select from this middle position, you will go to the digit which is even in a binary representation. This is a convention. It works. On average, it makes the banker not lose money and not win money either. Okay. When your routine can compute things at this level of accuracy, it is said to be the correct rounding. It is complicated to be sure that you have these 3 extra digits because in the silicon, the CPU can compute with these 3 extra digits, but you never see them. You see only the rounded result. And when you combine a lot of arithmetic operations, the IEEE standard guarantees you that plus, minus, times, and division, as well as the square root, are always rounded correctly. For all the rest, you have no guarantee. So if you want to be able to compute this level of accuracy, you need to take extra steps to be sure to have these 3 extra digits that you store nowhere. How do we do it? Good question. Which means that most of the time you get satisfied with 1 ULP, which is faithful rounding, not correct rounding, faithful rounding. And we should see it bluntly. Most of the time it's happy-go-lucky rounding. We have no idea of the accuracy of our computation. Nevertheless, the rounding, despite being strongly nonlinear, is completely deterministic. What is not deterministic is the order of the operation when you have concurrency. Okay, so the quantum of precision is the machine epsilon. The formal definition is the distance between 1 and the next representable floating point number. You can express it also as 1 ULP above 1 or the largest relative interval between two nearest numbers in finite precision. Typical values are 10 to the minus 10, which is 1 per 1,000 in half precision, 10 to the minus 7 for single, 2 to the minus 2 times 10 to the minus 16 for double. On quadruple, you can go to 34 decimal digits. So it's a measure of how close our floating point number can be before they merge into only one representable value. This is, in some sense, the resolution of our measurement instrument. Oh, some question, maybe? Where? Oui, ah ben c'est... Ooh, a lot of questions. No, okay. Yes. Fascinating. Do these sort of errors exist in an order of magnitude independent way? Okay, the detail, when you scale this kind of computation, will change slightly, but one point we have to deeply understand is floating point numbers are a multiplicative representation of numbers. So when you scale, the wrong behavior and the good behavior scale as well. So yes, the 10 to the power 18 will affect, 10 to the power minus 18 will affect because it is 10, but if you do .1 times 2 to the minus 18, if your scaling factor is a power of 2 instead of a power of 10, you will have strictly the same behavior. With a power of 10, you will have some more rounding error on top of this, but not something bigger. And for the last part of the question, would the answer change if a program is using Fortran 90 over Fortran 2.3? Yes, this units all of us, any of our language, we are mostly trapped, except maybe some people with strange FPGA. We are mostly trapped in IEEE 754. Okay. So to avoid the multiplicative effect of rounding behavior, we can use stuff like interval arithmetic library. Is it common? Okay, so I will say bad things about interval arithmetic libraries, but later. Yes?
Since you are suggesting the ULP depends on where you are in the floating number, like you are saying that it's a ULP after 1, but I mean, it's not intuitive why the ULP depends on where it is.
I'm suggesting ULPs.
Because you were saying that is a ULP, you were defining the machine epsilon as ULP after 1.
Yes.
So it seems you are suggesting the ULP depends where it is after, right?
Yes. Okay. So you have seen that this is a multiplicative representation. So one ULP after 1 billion has a larger scaling factor. It's a relative unit rather than an absolute unit. Does it answer your question? Yeah. Okay. And so in parts of science, we are more concerned about the relative uncertainty. And with this kind of number, what is easier to evaluate is the relative uncertainty. But of course, we can always display both. Okay, so every decimal is not a binary. Conversion to binary relies on rounding. No need to insist anymore. On the opposite way, every binary is a decimal. So yeah, we can represent exactly we can convert the number we have computed in binary in decimal. But nobody does it because we would have too many digits. Let's suppose we have some stupid format, but NVIDIA will do it one day, which would be FP3. We have 3 bits of mantissa, 4 with the leading one, on 1 bit of sign, FP4. Okay, it exists. So we can represent 1/8. In binary, it's the first bit below 0 is 1/2, 1/4, 1/8. Okay, it's good. So in decimal, you would encode it as 0.125. Okay? But this 1/8 means, in fact, in floating point, any number between 1/16 and 3/16. So in fact, you have between these two numbers 1/8 of ULP. It's a very big ULP in this FP4 standard. This would be bigger than the 0.025 in decimal. So we can only the first digit is meaningful. So when we will display in decimal this binary FP4 number, we'll encode it as 0.1. Because whatever you would display here would not be realistic given the accuracy of the format. So this is not obvious, but we can discuss it later. So when decimal is important, okay, now from C23, you can use this decimal 32, decimal 64, decimal 128 format. So if you are working in finance, SQL or COBOL are a good way to do proper decimal floating point computation. If it's only for money, you can count cents instead of euros. So if you need 2 exact places, you can rescale your computation and proceed with integer, and you solve the problem. And the general solution is use a fixed point format instead of floating point for any kind of financial operation or operation where decimal are important. It can be finance, but it can be anything where you have regulations that would impose you to have a very determined result. Okay, so let's go to non-finance application. We'll have function, we'll have sign, we do math. Okay, sign of pi, exact result, 0. You compute it in FP32, minus 8.74 10 to the minus 8. Come on, I have paid for this computer. FP64, 1.2 e to the minus 16. Come on. Okay, I have said that FP16 will suffer, but 10 to the minus 3, come on. It goes way better for cos of pi, provide the exact -1, even in FP16 with some. Why? Because next to pi, sine as a linear approximation, sine on pi has no exact representation. When you compute sine of pi, the mathematical one, you have 0, but your pi in the computer, even correctly rounded, is not the pi of mathematics. So the computer is right to tell you that it is not 0. And you can check that the discrepancy is of the order of the rounding of pi. Okay. So if this kind of thing is a problem, you have to reconsider your computation, use after trigonometric function. They exist in the library starting from C23 on Fortran 23. Instead of giving the argument as a number of radian, you give it as a number of half-turn. So pi is 1 half-turn, sin pi of 1 is 0, even in FP16. You can also use a trigonometric function in degree. They existed on all good Fortran compiler, but they are in the standard from Fortran 23. And this is not something as simple as I take my argument, I multiply it by some approximated version of pi, or multiply by 180 or divided by 180 times approximation of pi. No, they go into much stronger detail. Okay, we'll do sum. Sum are easy, it should be no problem. We'll do a large sum. We'll do some harmonic sum, the sum of reciprocal of natural number. And you have the asymptotic formula that it never converges, it diverges as a logarithm of your endpoint, plus the Euler-Maccheroni constant and some expansion as the inverse power of the endpoint. So I told you it would be bad for FP16. So we start with 250 elements, and I will have 3 columns. The first column, up sum, is when you sum sequentially one element on top of the other. The down sum will start from the top. We'll start with the small reciprocal, then piling up to the biggest one. And what I call the theoretical sum here is, in fact, what this asymptotic development provides you. So we see the up sum and the down sum are slightly different, which is still 2%, 0.5%. But the down sum is reasonably exact correct to the theoretical sum. You move further, and then the discrepancy gets bigger. We have a problem. But the down sum stays good. And then, after 1,000, the up sum stalls. You add things, and nothing changes. The down sums continue evaluating and staying quite faithful to the theoretical sum, and then after 8,000, it stalls as well. Whereas when you compute in single precision, you have valid results, even when everybody has lost the value in FP16. And you have to move up to 3 million to get some discrepancy between up and some down sum. So this phenomenon is what we call absorption. After some point, in our case, after 1,000 elements, 1 over 1,000 doesn't move more than half an ULP, the sum that you have up to that point. So you are adding something that is too small, and you add and add things that don't add up. When you start from the small value, you can absorb them. They don't get absorbed into this big ball of bits, and you can get a better result in this way. Yes, but tell me, I will not sort all my results before adding them. In my computation, the things I have to add don't come out sorted. It's nice if I have some idea of the order, but in the general case, so this is the example in modern Fortran. We can change the loop to use a compensated sum, so-called Can-Babushka method, where you use compensation on accumulator on temporary sum to keep track of what you are losing during the addition at each step. And the results are quite good, because these were the results before. This was the theoretical sum, which with only 62 as endpoint is not correct. The asymptotic development is not precise enough. So to have a more accurate result, I computed in double in this column. And I compared it with some exact computation with integer. These 4 digits are, even 5 digits are all correct, mathematically. So the Karen-Babushka sum, I tried it in one direction, up sum, and down sum. And what you see is the result doesn't depend on the ordering. So not only it does not depend on the ordering, but it's quite correct with respect to FP64. It's really no more different than 1 in 3. It fits with the theoretical sum, and it starts getting wrong after 32,000. Okay, this is the last point where it fits the theoretical sum, and it's a bit different from FP64. Okay, at some point, yes, 64,000, it's still quite good, but 128,000, it's wrong, because you can do so much with FP16. So if you want accuracy, you want higher precision. Okay, so let's try to go a bit above. We have a yes question. Machine epsilon benchmarking tools. The machine epsilon is something that depends on your format. If you have FP13, you know your machine epsilon. If you have FP32, 64, 16, 128, 80, it is fixed, one machine epsilon for one type of number. So if what you mean is, can I benchmark my computation against some expected result or theoretical result, the machine epsilon is your measuring tool in some sense. It's your ULP at the same time. And it's a relative tool. Okay. Explain more precisely what you want if I failed to answer. So result in slide 25. Okay, so I missed a lot. 25. Seemed to me that the calculation on cosine were closer to the actual value. Yes, okay. So no, there is no ChatGPT in this computation. It's IA3, it's natural stupidity. So why the cosine fits better? It's simple. Next to pi, the expansion of the cosine is like it's quadratic in the error. So if you are differing from pi from one machine epsilon, the cosine of your uncertainty of pi will be in square of machine epsilon. On the square of machine epsilon, it is not representable. It's as good as 0. So this is why linear approximation and quadratic approximation makes a difference. We will use this next to the end of this talk, when I will tell you about the kappa elasticity of a function. Okay. So, on the third question, how does it give a better result if some parts aren't added to the final output? Do you mean the Can-Babushka sum? So the Can-Babushka sum will keep track of the part that is lost in the rounding. But you can only go so far because at some point that we see here in 128,000, you are adding things that are smaller than the error on the rounding on the error. So you could have some two-level sum, but okay, use FP32 in this case. We can get protected from the vulnerabilities of the standard, but up to some point.
Yes, so if we take that to the next step, would it be possible to have a dynamically precise result for sums?
You can always use something more complicated than floating point. Okay. The point of using floating point is they are encoded in silico. They are the fastest possible way of computing things. We have seen that if we push things in the memory at the right time and the processor can process it without waiting, this is the best way we have in this world. This is inaccurate, but this is the fastest. If you want more exact things, you have the choice. GMP, rational number, interval arithmetic, stochastic number, a lot of solutions exist. They all are most costly. So this always is a kind of balance that you have to know. As most of us will be using floating point for most of the things, I share with you the experience of the things to do and to avoid. Okay, so we can define 4 classes of operation. Arithmetic, plus, minus, times, divided on the integer powers. All this, it is guaranteed by the standard. Maybe not the integer power, because when you take the square of the square of the square of the square, you will not have the correct rounding. The square of the square, you already lose the correct rounding because you have 2 elementary operations. So we'll see later why combining operation degrades the accuracy. Okay, but mostly arithmetic as well as the square root, which is already some algebraic operation in the sense of algebraic number that are solution to polynomial with integer coefficient, which means that roots of such polynomial are in the wide category of algebraic number. And for most of the algebraic number, we have no guarantee that the operation will be for most of the, not algebraic number, but algebraic operation, extracting roots, taking fractional power, all this can fail miserably. Okay, so what we call the elementary, which is elementary transcendental function, what we have seen in high school, exponential, log, sine, cos, irrational power, all trigonometry, including hyperbolic, all this, no guarantee. Some hope at some point, but very little. Higher transcendental function, so-called special function, Bessel, Airy, polylogarithm, elliptic integral, gamma function, zeta function, you name it. All this, you are in the wild. No idea about, most of the time, you are not looking if the last bit is good. You are looking if the last 10 bits are good. And so, why are these transcendental functions a problem? This is the so-called table maker's dilemma. The transcendental functions are costly. So if you ask around you, people will tell you, oh, we take a power series expansion, and that's good. It's a sum of product of power. It cannot be bad. But if you want to guarantee the last bit, you may need to compute 30 digits, 32 digits, to have the correct rounding at the level of the 16th. So Paul Zimmerman has example like this for exponential in double precision. So if you want to be exact as possible, it costs you an arm and a leg. You can see this if we want to have some poetry as a fact that rounding is nonlinear. It is mixing various scales. It starts runoff, butterfly effect. Okay, so this is nice in a party to discuss. Many times we want, we would think, okay, we'll have double rounding. This was very popular at the time of 32-bit Intel processor, because oh, you are too young. At that time, all the computation internally were performed with long double precision and then rounded. So every operation had 3 more decimal digits. And when they moved to 64-bit, they decided that, okay, nobody uses it, we don't care, we have no complaint, we get rid of this. It would introduce stranger bugs in your computation. When my colleague in Japan were comparing all the double precision workstation, Sun, HP, DEC, you name it, were giving consistently the same result on their computation. And the first time they started on Linux on Intel 32-bit, the result was different. So the conclusion was immediate. Linux is bad. And it took some time for me to understand that because of this subtle extra digit computation, the result would be different. But what we will not see today because it's too low level, you can switch some of the control bit of your floating point unit. You can ask, no, in fact, truncate everything at double precision and don't use this extra long double precision. And I could activate this and fall back on the correct, less correct mathematically, but more correct for them result. Nevertheless, we think of it as more correct, but the double rounding is not always the correct rounding. When you would round from long double to double and then from double to single, it's not the same thing as rounding directly from one to the other. So one has to be cautious. Breaking news. Okay, not so much breaking because it has been 1 year and a half. Paul Zimmerman and his team, please go look at its Lauria webpage, as well as the core math GitLab page .inria.fr. Succeeded in introducing correct rounding, some correct rounding, for the following functions. So arc cosine in single precision, arc hyperbolic cosine in floating point, single precision, arc sine, okay. So a lot of single precision functions are now correctly rounded. And what is important, it could succeed to put it in the libm, in the C library, because it was correctly rounded and faster than the previous version. So we have it as well for some very difficult functions like the log gamma function and the T gamma function, the error function in double precision. So we should support this effort. So please get prepared. Some of your colleagues will one day come to your office. I don't understand, I have changed nothing, the results are different. Yes, maybe now they are correctly rounded. We have a future with a very strange bug awaiting for us. Okay, so before getting to some other point, what is the essence to keep in mind here? If you can, I will expand on the essence to keep in mind, on the behavior to keep in mind with this respect. But closer to the end of this talk, on floating point calculation are inherently wrong, but they are the fastest type that we have at our disposal. What can we do to get performances while also getting the correct result at the same time? Okay, so this is a good take on what I'm telling you. So yes, if we want to have some mi-temps, half time, I would say in the first part of this talk, I have to make you aware of the difficulties. And we'll see moving inside this talk that there are some, maybe not solutions, but some behavior, as he said, to be taken, we have to take some measures.
If I would just answer this person is that, I mean, the choice here, now you represent or given us two representation, which is either binary or decimal, right? But I think to answer this person is to say that whatever base you choose to go with, even if it's 2 base or 10 base, or if it's pi based or whatever, you're still, for most applications, you're gonna get rounding. And if you I mean, you can choose to go to infinite precision, but then of course, the application will be infinitely slow as well. So I think, yeah.
Thank you. Does it mean muscle is worse than glibc from a floating point perspective? Okay, so okay, so correct rounding will move things by, in principle, 1 bit. Okay, but maybe more, because you had no guarantee before this what was the level of accuracy. If you look back in the 90s, the 3 last digit would be wrong. So now the last bit will be correct. So it's a lot of progress that we benefit from. Another point is not many people have yet glibc 241, 242, or 243 on their computer. So we have time for things to explode. Not everything will fall apart at the same time. On muscle, we'll certainly get the information, get the routines propagated. This is not the hardest part on the two-port. Okay, but okay, who needs double? People who have been too frightened. In physics, we don't need 16 digits. What is the best measurement we have? 12 digits on the mu G minus 2? 8, 10 digits, something like this? Okay. So, if we compute in single precision, real 32 here, oops, sorry, the Stefan constant, which is the ratio of total power absorbed, radiated per unit surface to force power of absolute temperature of black body. If you compute it with the formula, which is here, in single precision, it's not a number. So you need to rearrange the computation, packing things together, if you want to have the correct result. Okay, compared to more accurate result, this product of powers give us a 2 epsilon discrepancy. It's good. 2 epsilon, it's 10 to the minus 6. We are okay. Okay. So why do we have not a number? Any idea? Okay, Boltzmann to the 4. Boltzmann is 10 to the minus 23. To the 4, it's 10 to the minus 92, which is 0 in float. On light speed times 2 multiplied by Planck to the 3rd. Planck to the 3rd is 10 to the minus 102. So it is 0. So we have 0 over 0. Sigma is not a number.
Well, Boltzmann to the 4 is absorbed to 0, so you divide by 0, I think.
Boltzmann to the 4 is 0.
Yes, and so if you divide it by Planck, it's approximately 1 or something. It's close. It's 1 order of magnitude, so it becomes.
Planck to the 3rd is 0. Okay.
Yes, I mean yes.
What is below?
Yes.
Yes. So when you proceed like this and you force the order of evaluation, you get the right result because, yes. Thank you. So you know what I will be doing on the next slide. FP16. So in FP16, everything is nan. So even the slightly nicer way gives you a nan. So it's no use in computation. So when your physicist or scientist colleagues come to you and tell you, oh, I have seen that this FPGA, this GPU, it is really fast in FP16, we should turn out all our computation. Not so fast. Really not so fast. So, okay, now we'll address the hard part, catastrophic cancellation. So for this first slide, I do it in base 10 floating point. Another time, it's a stupid non-existing format with only 3 decimal digits, but to get the feeling of it. Don't worry, we'll go to binary later. Let's suppose that in this format, we have A is 334 and B is 333. When you compute the difference, on a computer, it's rounded minus, we get 0.01. We call this a cancellation because the relative accuracy is terrible. We have only one significant digit. We had 3 significant digits before, and the result of this computation has 1 significant digit. And this is the smallest representable number in this format. So it is really bad as far as representation is concerned. But this is a benign cancellation because even if it's rounded and we have lost all meaning, the rounded result is the mathematical result. So now we do the same thing with the square. Mathematically, you find 2/3 times 10 to the minus 2. And when you run the operation as a computer with this system would do, you find 0.1, which is 1/10 to the minus 1. So between the computer result and your exact mathematical result, there is 50% of relative error on the result. This is bad because in this system, we can have 1 part in 1,000 relative uncertainty. So 50% is bad, and it's 333 units in the last place. No digit is even correct. We call this a catastrophic cancellation. In both cases, we have cancellation. One is benign, one is catastrophic. If I were the boss, I would say, when does this occur? And how many digits are lost? And there is no generic solution. On top of this, using the square here provides us an overflow risk. I have not spoken of the exponent part here, but 3 to the 34 will be above 10. So if it's really floating point, we'll go above the limit. Okay, we want to avoid the overflow. Let's factorize this. We'll take the rounded sum times the rounded difference, which is the famed identity, and the rounded result goes exact. So we have one method. If possible, we should factorize operation. We don't see yet why, but at least it works. Yes, but Vincent, you told us about a stupid system in base 10. It's meaningless. Okay, in binary. And for one time, I will not say bad thing about FP16. If you have FP16, you can try it at home. It's not harmful. So we have a mantissa of 10 binary digits. Here is the representation of the number you should input for A. This is the way you compute it, and this is some decimal approximation. This is the same for B. So you have 1.416 and 1.415. The discrepancy is exactly 1 machine epsilon 1 over 1024. This is a cancellation. It has reduced the accuracy. Only 1 bit survived out of all this. It's a cancellation, but it's a benign one. The floating point result, once more, in a real floating point system, is exact. We do the same thing with square, and this time, another catastrophic cancellation. No digit is even correct. 41% of relative error. I thought that half precision would give me 1 part in 1,000, and then I have 40% of error. What is wrong? Let's factorize it. You do the computation, and then you have something which is not the exact result, but which is within a third of an ULP. So it is the correct rounding. You are as close as possible as the good result. So there is something. Yes, but Vincent, you know FP16, they are not reliable. It's not on every computer. Okay, I heard it. Let's take it with something real that you can test in C, FP32. Here, you start to see the process. We have some discrepancy of one machine epsilon. This is a cancellation, but a benign one. The floating point result is exact. And you go to the square, and you have 41% of relative error. Oh, the same thing, which is a ton of ULP. No digit is even correct. This is a catastrophic cancellation. Let's factorize it. Please try it at home. It works. Okay. So if you are not frightened by now, let's take it to the next level. After the catastrophic cancellation, the cursed cancellation. A polynomial, it's arithmetic. What could go wrong? So Siegfried Rump provided us with this polynomial. Okay, we have half on quarter, but it means up beside the division by 4, which will be exact in binary. There is only this part, which is the rational fraction that we can evaluate separately. And we take coprime integers argument. So integers, what could go wrong? Okay, we compute single precision, -6, 10 to the power 29. Surprised? Any comment? You want to complain? No? Okay. Let's look at double precision. Oh, we have lost 8 orders of magnitude. Yes, but we have kept the same sign. It's not too bad. Long double. Ooh, even more loss of order of magnitude. And the sign is not the same. Oh, we have a problem. Okay. Let's call for artillery support. Quadruple precision. Ah yes, we have lost 29 order of magnitude on the sign. Well, it cannot be false. Well, yes, too easy. Okay, the exact result is this fraction that you see here. Okay, the sign is minus. So even the quadruple precision wouldn't get the sign, but the order of magnitude was not too bad. I cannot do my computation in quadruple precision. If you compute this fraction in any even FP16 of the format, you will have a very accurate thing. So the solution to your computation has a good representation, but you were not able to access it with the simple arithmetic. The result cannot be computed in easy precision. So I tried in octuple, it works. So in quadruple, it fails, and then it fails. I mean, there is no correct digit. In octuple, you don't have 128 correct digits out of the 256. You have 256 correct digits in octuple precision. So this is strongly nonlinear. Okay, so how will we control the rounding error? Okay, what format did I not try up to now? You are really into computing. I did not try the decimal floating point. Okay, so decimal floating point, single precision decimal, -4, 10 to the 30. The order of magnitude is similarly strange, but what we have is 4.0000000. Decimal double precision, -3, 10 to the 21. The order of magnitude is also correct, but we have a large set of zeros. On decimal quadruple precision, it's the same as quadruple binary precision. Okay. All these zero in base 10 means all the bits have been deleted. We have had a strong cancellation between the different terms, and only one digit survive at the end. So if we looked at the binary representation of our binary floating point, maybe we would see the same thing. Okay, and this is what we see. This strange number, it's exactly 2 to the power 99, which means all the other bits got lost in the cancellation. In double precision, it's 2 to the power 70. All the other bits got lost. In long double, 8 is also the most significant bit. This is because the long doubles, they don't proceed like other. And there is some small bits that survive at the end. Okay. So the quad, there are bits everywhere, but they are all wrong. But okay, we have some trend. If we lose too many bits, maybe we can detect that something is at play. One more interesting thing is with quadruple precision, this value that we compute is exactly the value that we add at the end, which means that all the polynomial part got cancelled in some way. So in the other precision, it got cancelled to some extent, and it overwrote the small rational fraction. But here, only this part survived. Yes, okay, so we know the solution. Now we should factor everything. Polynomial with two variables. Can we factor it? Okay, so we tend to simplify. I told you it's 1/3 integer times the cube of big Y is the square of small y. Okay, well, this polynomial should not be complicated. So let's take Macaulay, geometric algebra program, and try to factor it in the real. It doesn't work in the complex. It doesn't work in the projective complex because you have to homogenize this polynomial if you want to see the truth. It doesn't work. This is so-called irreducible polynomial. And this is a simple one. With the formula you have in your program, you don't have the time to go that far and try to factor things potentially with no success. So all hope is gone on this RAM polynomial, but it is designed to get frightened. Okay, so if we want to evaluate 1D polynomial, at least we can do something. There is the computational cost of all the exponentiation. If you compute it in the easy way, A0 plus A1 times X plus A2 times X squared, you are computing multiple times the product of X, so you would need to do it in some clever way to have your exponentiation taking less operation. The first theorem of algebra tells us that we can always factor it in the complex number. Okay. We can in principle, but in practice, it's another problem. On the real number, because we don't want to introduce complex in our float computation, we can have part of monomials times a quadratic part, but also it's complicated. The practical way to proceed is the so-called Horner-Ruffini polynomial evaluation, or Horner scheme, A0 plus x times the rest of the polynomial, in which you have A1 plus x times the rest of the polynomial. This is the right way for speed and accuracy. It's a guarantee of stability on the result and the safety against intermediate overshoot. On top of this, this scheme can use the multiply accumulate machine instruction, the FMA, that we have already spoken about. And for this kind of polynomial evaluation, in the same way as the Kahn summation algorithm, Kahn-Babushka, and its colleague Neumayer, and the combined algorithm Neumayer-Kahn-Babushka, you can do it also with dot products and with this kind of polynomial evaluation. So if you need accurate result on polynomial evaluation, okay, if you don't need accurate result, use Horner. If you need accurate result, use Horner. Okay, but who computes polynomial? What we do in the real world, we compute variance for uncertainty. We have statistical state of data. The first thing more complicated than the average value is the variance, which is a difference of square of sums and sum of square. All the problem we have seen. Sums, square, difference of square, it will go wrong at every step. So you have the two passes approach. You start by computing the average. You subtract the average to each of your elements in the second pass, take the square of this element minus the average, and you square. But when you are online, when the result comes and you have not enough memory to store them and you don't have the time to go back to the start, if you have some idea of the average, you can proceed to an arbitrary data shift because the variance is a translation invariant. Okay, and if you have really no idea of this expected average value, you take the one-pass online Welford algorithm. It costs you one more division per iteration. But the rule of thumb we had when I was a master student was never compute the variance in single precision. At the time, FP16 did not even exist, so okay. You at least compute a variance in double precision, or long double or quadruple, but no less than that. Okay, so what kind of other typical computation do we have? We have the dot product. Yes. We are late. We have the convolution product, or backwards dot product. We have the Fourier transform, which is also some kind of dot product. And the matrix product is a matrix of dot product. So dot product. So we can't use the factorization truck. It turns to be a sum of simple products, which are quadratic in essence. So we expect to encounter problems similar to difference of square and variance computation. But here we can't use the factorization tricks. So we have mixed precision as a possibility. We have fuse multiply and accumulate. We have fuse multiply and accumulate used to extract the two parts of the product. If you have a multiplication of 23 digits times 23 digits, you will need 46 places in the accumulator to have some exact result. This is what FMAT does. It has a special register which is twice as long to have exact result before doing the addition, and then only after it rounds to 23. And so you can combine all these techniques with can sum, compensated sum for dot product. Okay, so one very useful application is when you want to compare float. Comparing float is essentially organizing a catastrophic cancellation. If your two floats are equal, it means that you take one, you take the other, you subtract. The first bit goes 0, the next goes 0, the next. Every bit got suppressed. So you may think we want to avoid catastrophic cancellation, but in 10% of the line of your code, you are explicitly getting catastrophic cancellation and you want it. So at this point, we have to pause and look back to what are we doing? Because A minus B is not what we have in the computer as A, minus rounded what we have in the computer as B. So the mathematical result is the rounded result plus the uncertainty due to rounding, plus the uncertainty on the rounding of A, plus minus the uncertainty of the rounding of B. So when you want, if in your program there is if A equal to 0.2, what does it mean? Do we want it is close to 0.2? It is numerically exactly equal to something that I cannot represent in my system? Okay, so let's multiply the terms by 5. So if 5 times A is equal to 1, then it's good. But it will not work because of the uncertainty on the representation of A. So you can try to trick the computer, but it will not work. It's even worse when we have is A equal to pi. At least at this time, we know it will not work. But it doesn't work much different for 0.2. Okay, so even in the case where it should work, is A equal to 2? We have no representation error on 2. All the integers up to 2 to the power 23, 2 to the power 24, minus 1, can get an exact representation in floating point single precision. When you go to 2 to the power 24 plus 1, it will be rounded to 2 to the power 24. So sad. 2 to the power 25 plus 3 will be rounded to 2 to the power 25. Down. 2 to the power 25 plus 4. But okay, 2, no representation error. But then we know that there have been likely rounding error on A. So when the warning are on the compiler tells you, oh, you are comparing a float, it's bad. It's bad. You have to express things differently. So the usual way will be to ask, instead of the strict equality, that the distance is below some threshold. And this threshold cannot be arbitrarily small, but we have to understand that what we want to do, in fact, is a relative comparison. We want not some absolute comparison. You have it in many good libraries. It's not completely a problem, but what you are really trying to know when you look for very strict equality is to get something that is below. So this epsilon here is not the round epsilon machine. So we take some relative uncertainty, we multiply it by the max value of the two number, of the absolute value of the two number that we have. And this is the right way to express what you want. Except when b is equal to 0. Because in this case, if you want to compare something to 0, it means with the previous formula that absolute value of A is below epsilon the absolute value of A. So it doesn't match. You will never have it. We get an impossible constraint that only an exact 0 can match. So when we want to compare to 0, we fall back to absolute uncertainty, to eta instead of epsilon. And this eta cannot be arbitrarily small. Each floating point has the tiniest possible non-null normal value. So I give you some example of tiny, which is the tiniest normal number. Epsilon machine, which is the relative uncertainty. If you multiply epsilon times tiny, you find the smallest possible denormal number. So this number can be represented. Maybe we don't want to use it, as we will see. Okay, if you are trying to get something that is below this epsilon times tiny, there is only one possibility, it's exactly 0. So is it what you really are looking for? Okay, so we have to take into account what is the meaning of the comparison we are doing. We want to test whether the argument is in the domain of the function. A equals 0 to avoid computing 1 over A bigger than 0 to avoid computing the square root of A strictly bigger than 0 to avoid computing the log of A. Okay, so before using A to test something, you have to already have some idea of the uncertainty on A. And we will have a lot of tests to do because we want unit test. And unit test with float is prone to all these kind of problems. So I already mentioned it yesterday when trying to test the stencil. Okay, if you want to try to test your sign function, your special function with some value, is the value representable? Is the argument representable? So there is some thought to be given to it. Okay, so I've talked a bit about denormal, or it was called subnormal before, but it's no more politically correct. So below 10 to the 38 for FP32, below 300, 10 to the minus 338 for 64, and so on. So why did people get so much energy to put in the silicon of all our computer this kind of stupidly tiny details? Because it makes numerical algorithm and linear algebra algorithm much more stable when you reach kind of cancellation that you have in Gauss pivot and so on. So it has some usage. So this is why we have them. Why we don't want them? So Pierre conducted some tests about the time when you have some fraction of the normal number into your process. It's independent of the number of elements over which you do the computation. But if you have 0% of the normal, you have this bottom line rather fast, something like 3 elapsed time nanosecond per element. And as you increase the number of the normals, up to 100% of your number being the normal, you have been moving from 3 nanoseconds per element to 110. A factor 100 slowdown. Whew. Yes, but this is too specific, Pierre. It's not a bit exaggerated. Okay, so how could we get this number, the normal? So thanks to Adrien, he found at least 2 ways. Okay, the one that will not appear often is when you have the difference around the minimum normal threshold, but you already need to be around here. But the more realistic approach is whenever you have some geometric progression, whenever you have some exponential behavior in your computation. You mean we have some exponential behavior at play? Alors, bon, c'est pas là. Non. Il le fait exprès ou quoi? Ok, je sais. You have seen this movie. I like the director. Okay, so what we see on your left is the process of computing the Gray-Scott reaction, where we have added some halo here, which is to represent the area where we have denormal number. Okay, so let's start again. So you see that the number of the normal is increasing, the ring is dilating, and what we see on top is when we evaluate this process over time on some Intel processor, and what you see for the different curves, so this curve that is decreasing is the number of cells that have value 0. Okay, on this one, starting from 0 and increasing, is the number of cells that have a denormal value. And you see it's increasing rather directly up to some point that we have crossed where it reduces because the denormal gets pushed over the top. And then at the end, all the denormal are disappearing. You see the blue curve, and they fade in the end. What you see in this orange curve is the number of cycles consummated per cell. And you see that the computation cost is increasing from the start up to some plateau. And when the number of denormal is decreasing, the computation time gets decreasing as well. Okay. So what is this light blue curve? It is when we tell the processor, okay, don't bother, when there is a denormal number, it's 0. So when you don't compute the denormal number, the time used is flat. So there is another effect. The number of cells with 0 value that are at the maximum at start and decreases. The more 0 you have, the faster is your computation. Because the floating point unit knows that, oh, multiplying by 0, not even time to bother it, it's 0. So details about the floating point can have impact on your performance. Some people got very clever in AMD because on an AMD core, if you cut, or whether you cut or not the denormal, the result is the same. They are not affected. They implemented the electronic better. Okay, so we can see it in more detail. So these are the two curves, and when you move from one to another, okay, you see that the number of 0 and the number of subnormal is indeed the same, but with AMD, you have a constant cycle per cell. You can see it on some other histogram. If you keep the subnormal on the Intel processor, or if you cut the subnormal on the Intel processor, the number of cycles per cell has 2 peaks with subnormal because here it is at start. We have not a lot of denormals. And we have a fast cycle of computation. On the number of denormal increasing, we have items getting more and more cycle on a big peak of slow computation when we have the maximum number of denormals. But when you cut their computation, you have a much more concentrated peak at less than 4 nanoseconds per cell, 4 cycles per cell. Thank you, Sébastien. A bit of unwaving the mass, okay. We know the wave equation, the heat equation. We are in some kind of heat equation, so we have the diffusivity which is this alpha factor that we have in our equation. It's not for heat, it's for concentration, but if we are looking for plane wave solution, because when you have a linear equation, you Fourierize it, then you get some dispersion relation, which in our case, as in Fourier, has both a real and imaginary component. On the Gray-Scott reaction, it cannot be solved because it is nonlinear. But when your nonlinear term is epsilon machine, you don't care. So when you are on the ring at the outer place of your simulation space, you can solve the linear equation, and you can find some Bessel, cylindrical Bessel solution. On this decreasing wavy exponential that we have seen here will be a geometric progression towards the normal number. This is why we can get the normal number in this apparently not dangerous computation. Would you suffer 10 more minutes? Okay, so this is the best part, but usually it gets cut. It gets cut. Quadratic equation, we have seen it in high school. 4,000 years of history of the quadratic equation. What could go wrong? Okay, so now we have some feeling about it. There are at least two possible catastrophic cancellations in this expression. You have a sum here. If beta b on square of delta get close, it can be not so good. And inside the delta, you also have some subtraction, so it's not so good. So my first lecture in numerical analysis taught me that we compute the big root with summing minus b on the square root of delta if they have the same sign, and minus b on minus square root of delta if they have the same sign. And then we compute this value, which is the sum of same sign value. We compute one of the radix this way, the standard way, and we compute the other radix as the invert of this. This is from the 18th century. The Count Fagnano found it, looking for small radix, small root. He inverted the equation. He took the equation of the reciprocal, and the two equations share the same invariant. So there is something deep about this connection, and you find it in any good textbook. You even find it in numerical recipes. It has been promoted from 2 centuries ago, so 250 years ago. Okay? You can go even further, because as scientists, you have all been told about dimension equation, about homogeneity. But I don't know anybody who applied it to the quadratic equation, except Middlebrook. In your quadratic equation, if x has some dimension, then A, B, and C will have a different dimension. So we have some factor B over A scaling with the dimension of x, some factor C over B which also has a dimension of x, and some dimensionless number which is the shape parameter of the solution. And then the solution of your quadratic equation is this formula, which is so-called low entropy formula. So depending on some sign, you can have this way to express it, because if sigma is positive, then you have the difference of squares, so you factor it. You know you have to factor it. In the opposite case, you can extract a thing with the FMA to be extra accurate, but okay. These are the results. And it tells us that we should always try to look at the dimensionless number in our problem. Before putting your computation in a computer, you should look at the meaningful scales and have all your computation done with non-dimensioned equation. The function f in question, you see, it moves from, the range moves from 0 to 1/2, and f is moving from 1 to 1/2, so only one bit of dynamic. You don't change the exponent. You are at the place where only the mantissa is at play, and you are far from any cancellation. But you see that next to the end part, you may have some cancellation between 1 and -4q squared. In order to have some idea about will my computation go wrong, you compute your factor q, and when q is next to 1/2, you know it will be wrong. So I have no time to go into more detail about what is the kappa factor. So for each of your formula, if of each of your function, you can, not always easily, but you can compute the so-called function elasticity. And in this case, the function elasticity, depending on your factor q, tells you that when q is below 0.4, you are not losing accuracy. You start losing accuracy above 0.4 something, and at most, you will be losing 5 bits of accuracy. That's honest. So I didn't prove why. Don't hesitate asking questions later at the coffee also. So to summarize, dimensional analysis on your formula will split the scale parameter that you can multiply your result at the end when you need to display it on the dimensionless shape parameter that are pure number and that tells you about the reality of the numerical problem. Middlebrook does not explicit what is the entropy of a formula, but when you look at the solution of the quadratic equation, you say 3 parameters, it will be difficult. In fact, the solution depends on only 1 parameter. You may understand this formula entropy in this sense, less real problem parameter. Scale parameters are not a problem. You can always multiply or divide. There are often many ways to do your dimensional analysis, depending on the problem symmetry, limit the computation complexity, but it brings all the value you compute close to your unity where the floating point density is higher, and you are far from overflow, and you are far from underflow. Okay, quick example about the subtraction. Colleagues in astronomy use regularly this formula in their Compton detector, depending on the energy deposited in the calorimeter. on the energy deposited in the first plane of detector. With your exert I, you see that in fact this part is negative, so you are subtracting something from 1. So the right way is to see that there are 2 subtraction of things of the same sign. With basic algebra, you get rid of this subtraction. So, by the way, this is dimensionless. And you keep only 1 remaining same sign subtraction, but then you use basic trigonometry. You have the formula for cosine of 2 alpha. And now you have a formula with only 1 dimensionless parameter, the square root of this parameter, the arc sign, which has the correct rounding in glibc 241. So you can get as exact as you can with this, whereas here you can have problem of cancellation. So in this formula, you have no problem of cancellation. So as it is where I am way over time, I will go to the conclusion. You have avoided a lot of formula. And I couldn't speak of Canada. So, yes, we go to the conclusion. Okay. So now you know your enemies, plus and minus. But you know them. You can keep calm, cool, and collected. As X. Cassidy does it, precise number plus precise number is slightly less precise number. To multiply them, it's also slightly less precise. Precise number plus garbage is garbage. Precise number times garbage is garbage. Square root of garbage is less bad garbage. Square of garbage is much worse garbage. The sum of garbage is better garbage, if it's statistically independent. Putting a precise number to a garbage power is a much worse garbage. When you suppress, cancel 2 garbage, it's much worse garbage. You know it, I spoke about it all along. You can even have this causing a division by 0. So the only way to have some precise computation is to multiply by 0. Thank you.
Wrong timing. The auditorium is too long. So thank you, everyone. Thank you, Vincent, for the nice presentation. Hope you learned a lot during this presentation. So that's all for today. So thank you, everyone, for attending the school in the satellite sites everywhere. We'll continue the magic tomorrow because it's a bit too much to continue right now. So we'll do some magic with Python tomorrow. So Numpy and all the derivative of it. So hopefully you will also learn a lot of stuff. So see you tomorrow.